All right, we are now recording, so from what we do now, and the rest of it will be out there on YouTube sometime either late this evening, sometime tomorrow, okay? Don't know exactly when, but it'll be there. So let's talk a little bit about maybe first how you get to it. Are all of you familiar with Blackboard? Okay, somewhat. Okay, I saw that. Okay. All right. When you go to this course in Blackboard, the home page there's a block right up here, upper left corner. I can't remember what the first thing is. It may be home page. I don't want to say something like that. Usually the second or third block, see, I only see the instructor side. I don't see the student side, so it may be a little different there. But there's a tab there called Content. If you go to Content in this course, then it'll open up and you'll see about 4 things there, I believe. The first one will be the syllabus. So what we're looking at here is loaded in Blackboard there. So you can see it. The next thing in there will be the research paper general instructions, which is the next thing we're going to talk about. The third thing will be my locator card showing when I'm in class and when I'm not in class, when I'm on campus, not on campus. That type of thing. We'll go over that here, but you'll see it there too. And then the fourth thing will be the link to YouTube, okay? And this package, Screencast-O-Matic, is recording everything that's projected and everything I'm saying in sync, and you'll be able to go back and review that if you want to. Now, that's all under Content, okay? And those are 4 different things. I'm trying to remember if I have any additional. What I haven't done yet is put the PowerPoints on there, but I'll put those under Content as well. Okay. Every chapter has a file of PowerPoint, so if you want to print those out before class, take notes on them, or whatever you want to do with them, they'll be there for you. Okay. And then if other students have sent me files they found useful in the course, I'll put those out there too. I just don't recall that I've received any for this course. For the Physical Science 111, I had a few on astronomy and that kind of stuff that were really nifty. But for this course, I just can't recall any. There may or may not be some. You'll see them if they are. Okay? They're not there yet. I've still got to find those. Okay. Any questions about how to access what we're going to be doing? Okay. That's all there. Now, this is your syllabus. Now, I had my work study student make the changes, so if I find any errors, it's going to be his fault, not mine. No. Okay, we'll see. This is fall term 2016, mini term 2, Physical Science 112, Physical Science 2. Now, that's something a little strange here. The state of Alabama calls Astronomy and Earth Science Physical Science 1 and calls Physics and Chemistry Physical Science 2. But every physical science book that I can think of that I've seen always has physics and chemistry in the first half of the book and astronomy and earth science in the second half of the book. So evidently the rest of the world does physical science 1, physics and chemistry, and 2 is astronomy and earth science. We just do it a little backwards. That's why we're physical science 2 and it's 112. You don't need one to take the other. Now, Nick has had 111, right? And nothing in 111 is useful here. Actually, more of the stuff this would have been useful in 111, but not that much. Okay. The course hours is a 4-credit hour course, 3 theory hours, 1 lab credit hours, even though we're in lab in a regular term 2 hours a week, in a mini term 4 hours a week. Okay. In class 3 theory credit hours a week, which really comes out 2.5, but because it's mini term, that's 5 credit hours a week. Theory credit hours a week. So it's compressed. Every day of class is like a week of class in a regular term. But y'all are used to that. Y'all do mini terms, okay? So please don't try to miss this. Technically, on a full term, 5 contact hours a week. In here, it's closer to 10. It's actually 9. 4.5. Okay, can I get your name, please? Powell? Okay. No problem. And what do you go by? Powell? Not Siegfried? Okay. Okay. All right. I can pronounce Siegfried. Okay. Huh? Which do you prefer? Which do you prefer? No, no problem. I wanted to call you late. So, okay. What's your go by? Siegfried. Okay. All right. Okay. Although I feel like I'd have to call you Mr. Powell if I called you Powell. No, I'm just kidding. Okay. All right. We try to hide from people, but we didn't succeed. I mean, it just, yeah, okay. All right, we're just going over the syllabus, and as I was telling the others, everything that we do in class and much of what we do in lab, I try to record in a package, not a very good package, called Screencast-O-Matic. So everything will be recorded and then put on YouTube. And it's already a link in Blackboard for you to get there under content. Nothing is there yet. Now, the syllabus, research paper instructions, and my locator card are out there, but I don't have the PowerPoints yet, and I don't have, and I have the link to the playlist in YouTube, but nothing's in it yet because we're having the first class. Okay, so we meet for close to 9 hours a week, okay? Not quite 5 contact hours, but 4.5 a day, which is like a full week. The meeting times, as you know, are Tuesday, Thursday, 3:15 to 5:45. That's usually going to be the class time, and it's here in this room. The lab, Tuesday, Thursday, 5:45 to 7:45, and for most of the time we'll be here. Well, I say, at least some of the times we'll be here in this room, okay? Other times we'll go to a lab close by, 353, 253 or 259 probably would be the ones. We might go to 252 if both of those are being used, but we'll see, okay? But some of the labs will be here, some will be elsewhere. We'll handle that as we go. Now, today's going to be a little different because we've got all this stuff at the beginning. This is technically going to be our lab time, and then when we finish all this, then we'll get into the class time, okay? So we're sort of turning things around. Now, in future days, I can't swear we'll have a lab every day, but it's going to come pretty close to it. But I like to cover the material that's going to be covered on the lab before we do the lab. I found it so frustrating when I was in college and doing a course like physics or chemistry or something like that, and we would have a lab, but the lab would be ahead of the class, and I wouldn't know what they were trying to get across in the lab, and later find out, oh, that's what they wanted us to learn there, but, you know, because it was all crossed up. So I always try to cover the stuff in class first and then have the lab. So if we finish something, say, at 6:15 one day, but we don't have 2 hours for lab, we'll have the lab the next day. And we'll go on and cover new material till 7:45 and then make sure we have the lab then. Now, when it's test time, what I like to do there is put the test the very last thing. I'll always give you at least half an hour, wasn't it, to do the test. And I don't think you'll ever take that long. But I do that at the end so you don't have to sit around waiting for other people to finish the test and then pick up class again. So what we'll do, whenever we're going to have, except for today, we'll have class first, lab second, and then test third if there's a test, okay, and if there's a lab. That way, if the lab's the last thing, when you finish the lab, you can leave. You don't have to sit around and wait, and then we start class again. Or if the test, as soon as you finish the test, you can leave. So I found it's just easier, better for y'all if that, rather than, well, we have the test now, and then you'll have to wait 45 minutes till everybody finishes it, and then we'll pick up class again. That just doesn't work as well. All right, my name is Charles Fowler, and one of the reasons I was late today, I'm also the math department chair, and I had a student who was a transient student from UAB trying to get in a second mini-term class, but UAB hadn't given her a transmit letter in time, and now it was too late, and they had to have special permission. The instructor wasn't available. It was just a mess. So every now and then I'll get caught in something like that, and that's why I was a few minutes late getting here today, because I basically called my boss and said, can you handle this, because I've got to go to class. and he was real good about doing that. So anyway, my contact policy. Here's my phone number, 929-3449. Okay? This sounds terrible, but it's true, so I'll go on and say it. If I'm not in the office, if you leave me a message, I don't know when I'm going to get to it. Right now, I'm so far behind in voicemails, I'm not even sure if I'll ever hear them all. I'm getting too old to, But anyway, try to call me during office hours, and you're going to see what those are coming up right away. Try to call me during office hours. If it's not during office hours, I'm more than likely not in the office, and I may not hear the voice message for a while, okay? Email, right now I'm a little bit behind in email too, but I will see those sooner than I'll see that. I mean, we communicated a little bit by email, so I'll try to see those, but I'll miss some of those too. My office is room 265. I don't know if you know where that is, but if you go out the door here, down the half flight of stairs, and go almost to the end of the hall, before you run into the concrete block wall at the end, there's a stairwell right there, okay? Just before the stairwell is my office. It's in between a mechanical room, a fan room, and the stairwell, 265, okay? So you can see me there. It's right across from the orientation classroom. If you've taken orientation here, right across the hall from that. Next door to 263 is the classroom, but then the fan room and then the office. Okay, now on Fridays, I'm on the Birmingham campus most Fridays, and I'm in the academic building, B122, and by the way, that's Dr. Pruitt's office suite, okay? When you go into it, you'll see his secretary sitting right there. He's in the back corner office. There's a little closet, no, it's a little room, a copy room really, right behind Ms. Saxon's desk. That's where I am. My same phone number works on both campuses, so during office hours, catch me there. So that's on the Birmingham campus. Now here are my office hours, or at least as best I know them now. On Mondays and Wednesday mornings, I have an 8 o'clock class and a 9:30 class. And then I have lunch/office hours from 11:15 until 12:15. And then I have another class starting at 12:15 that goes until 2:55. And then I'm supposed to leave at, 1:55. And technically I'm supposed to leave at 2 o'clock on Monday, Wednesday. Okay? I don't. So I will be in the office after 2 o'clock. Most days probably till 4:45. Some days maybe as late as 5:15. Some days I may have to leave earlier, but I'm technically supposed to be out of here at 2. There's no way I'll be out by 2. So if you need me Monday, Wednesday, try to get me as soon after 2 as you can. Okay? I will probably be in the office for a while. On Tuesday and Thursday, I have an 8 o'clock class, a 9:30 class, and an 11 o'clock class. And that gets through at 12:15. And then I'm in the office, and eat my lunch in my office until 3:15 when this class starts. And then I'm here until 7:45, okay? I have 15 more minutes of office hours if you need to see me. But yeah, as you can see me, between class and lab, before class, after class, I'll hang around if we need me, okay? On Fridays, I'm usually in 7:45 to 11:45. No classes, and that's on the Birmingham campus most Fridays. But the same phone number works, but I'm there in room B122. Now, let me say this about Fridays. They love calling meetings on Fridays, okay? So it may be, and if I know I've got a meeting coming up, I'll let you know. So you don't make a trip over there just to find out I'm not there. But I also tell you this, I hate sort of to say it, but it doesn't matter. I have a mild form of leukemia, so I have to have treatments periodically. And I'm starting a new drug, not this Friday, but the following Friday. So there's, get this, 300 milligrams of drug they're going to put in over a 7-hour period, okay? They're wanting to make sure there's no reactions because I've never had this one before. So Friday, this Friday I'll be there, next Friday I won't. Then the next week, if I handle the treatment okay the first Friday, then they give me a full treatment, which is 1,000 milligrams, 1,000 milligrams, okay? And again, they say it could be 6 to 7 hours. If it seems like I handle that okay, then they'll speed it up and probably only be 2 or 3 or 4 hours, you know. But it'll be every 2 months from then on. So once I get it done in the next 2 weeks, then I won't have it again for 2 more months, and more than likely the term will be over by then. So anyway, some Fridays I won't be there, but I'll let you know ahead of time. Just like I'm telling you now, but I'll let you know. I won't be on campus. I will be there this Friday, but not the next 2. Okay, the course description. Now, this isn't something I made up or anyone here at the college made up. This was done by a committee made up of 2-year college system and 4-year colleges and universities in the state of Alabama, and they've decided if we teach this, they give you credit for it if you're transferring. This course provides the non-technical student, now don't get offended, I know the automotive students are very technical, but meaning non-engineering type students, with an introduction to the basic principles of chemistry and physics. Now we'll do it in the reverse order, we'll do physics and then chemistry. Laboratory is required, and we've already talked about that. All right. The prerequisites for the course, really none. There is a little math involved, but it's probably not past 098. And my guess is most of you have already gone past that, right? Even if you haven't, I don't think you'll find it difficult, okay? And actually, the most math is going to be on this first chapter, okay? So we'll hit it, but then after that, there will be little bits, and there will be problems all throughout, and there will be maybe 1 or 2 things in each chapter after that, but really, a lot of chapters, not too much. Okay, the textbook is this one, okay? Now, you may have an earlier edition. What edition is yours?
7.
The what?
7.
7, okay? This is the 10th. I don't think you'll find hardly a dime's worth of difference between the 2, okay? The chapters are the same. The only reason they update editions so frequently is so they can sell new books.
That one is $200-something on Amazon. This is $6.
Okay, good choice, okay? I've taught from that one too, and there's hardly any difference. Okay, show that one. Did you find it in the bookstore? Okay, they had just maybe 7 of these, or how many would you guess? Huh? 6 or 7 of those. If you get that, that's the cheapest, okay? They're used, and that's probably from I think that was from the 9th edition. So the edition doesn't matter, okay? But that's going to be the cheapest. That's only the chapters we're going to cover. This is everything in Physical Science 111 and 112 in chapters we don't cover in either one. Okay, now that they had in the bookstore, I didn't order that. I don't know how they got that. So take it back and get your money back and see if you can get a textbook. That's the lab manual. Yeah. I'm sorry, I can't. Right. Mm-hmm. See, I'm hard of hearing. It's not y'all. I'm hard of hearing.
They won't return the books back. They won't let you return them.
Because when I showed with me, they just wanted to see my schedule.
Yeah.
And they gave me a little card too. See, I had to log into my lab.
Okay. Okay. I did not order the book, and I told them in the bookstore I didn't order the book, and I said the students don't need the book, so I will talk with the bookstore and see about giving that back. Okay. Now that's the other option. That may even be cheaper than the book. Okay. How much did that cost? Oh, with the lab manual? Yeah. Okay. Okay. They thought that y'all wanted to go ebooks. And I said,
that's what they were selling. Yeah,
right. Right. And I went by last week and I found this out first time. And I went, where did this come from? And they couldn't tell me. I said, I did not order these. I did not order the lab manuals because I give you the labs. We use a lot of labs out of there, but I make copies for you. You don't have to have that. Other labs I make up myself, and because they fit better than what we need. But if that's the only way you could get that, then that may be why they won't take the book back. I don't know. So I told them they needed to order books, not just ebooks. Now, if you want the ebook, you can go that route. Okay?
Yeah.
See, we've got a new company. It used to be the bookstore was run by Lawson State. Now there's a company, what is it, Hibbett or Follett Books. They run the bookstore, and they seem pretty good. They seem very agreeable. When I found that out, I said, look, we need the textbook. He said, we'll do a special order and get it there overnight. So I went by Monday. They said, well, they didn't get the thing sent off in time, so it'll come in today. Where the big books weren't there? Okay. But I told them, I said, do you have any of these left? They said, we have a few back here. I said, put them on the shelves. That will be fine for the students. So they brought them out and put them on. But they only had, like you said, 6 or 7. So they've got them coming in. If you prefer ebook, they have the ebooks right now. Okay? You do not need to buy the lab manual. Okay? Now, they may be requiring you to buy the lab manual to get the ebook. If that's the case, then you'll have to work that out. But they do have the books coming in. They told me they would be here by the day, but evidently they told me it was going to be here by yesterday. But
I've dealt with that all year with them. They tell you something, and they never get it in.
okay, well, he said they were going to overnight them on Friday, and they weren't here Monday. He said, well, they didn't get the order off in time, so they'll be here by tomorrow. But I didn't get a chance to go by today. The author is Bill Tillery for everything. Okay, Bill Tillery. And you said you got yours on Amazon, an older edition for $6. That's sufficient.
It covers this class and the 111.
Yeah. Okay.
I can buy both of these for $60.
Yeah. Okay. So if you want to go that route, that's cheap too. They also have rental, which is cheaper than buy. Okay. So there's lots of options there, but you do not need the lab manual. I told them that, but I think I know what they're doing. They're selling the Connect card, but making you buy the lab manual with it. I bet you that's what it is. That's something the company talked them into, not me. Okay. Any of the later editions too, you can probably get them. Maybe not for $6, maybe for $12.
Yeah, it's still on there. She did it.
Oh, she did. Okay.
$6.21.
Okay. Boy, you big spenders, you. Okay.
It was on there.
Okay.
What edition?
Okay. Again, very little is changed in the edition, from one edition to the other. Page numbers may have changed, so when I refer to a page number, you just keep searching till you find it. Okay. Sorry about this, folks. Okay. I'll see what I can do to get them to take the lab manuals back, because you don't need them. I told them that. But I didn't find out until just before it was the end of last mini term when I went down to check. I said, what are these doing here? Okay, the 10th edition one I have is 2014. The others are just a few years before that. Nothing much has changed in the material. Students are expected to bring a textbook, whichever it has, maybe not today, paper, pencil to class each meeting. We will be working problems. You will find the calculator handy. Okay, you won't have to have one. They certainly will help. And you can certainly use calculators for every test. Now, I usually say this later, but while I'm thinking about it, let me say it now. For every test in this class, you can bring with you a formula and equation sheet. That's what I call it. Anything you want to write down on a piece of paper, front and back, as small as you want to write it, you can bring a piece of paper to class for every test, including the final exam. Okay? So I don't believe in memorizing. I don't like memorizing. I'm not a memorizer, but I want you to know concepts. And frankly, I think that's a good idea in any class you take. Write yourself a formula and equation sheet. I found when I was in college, decades ago, it's not that funny. Okay, very seldom did a professor let us do that, but when they did, oh boy, that night before I was organizing my stuff, writing everything down, making sure I got all the information I thought I would need, and wrote it all down, and then I go in to take the test the next day and forget to look at it, because that was the best review and study I could have done, was writing the stuff down. I could look at the stuff all day long. That's shallow memory, okay? Writing it down, that's deep learning. Okay, so it's a great idea to do, even in a class you can't use it. Do a formula and equation sheet. But you can use it in this class. Okay, now this next paragraph, they say we can't touch it. Okay, I don't like many things in it. I'll also say community college students must be trained in Blackboard and use Blackboard daily to gain access to vital course information such as the syllabus. And y'all are going to read the syllabus every day, aren't you? Oh, yes. Saturdays and Sundays included, right? I'm kidding, okay. I'm making fun of them, okay. Okay. The syllabus is out there, so you can see it anytime you want it, even if you want to read it daily, okay. Handouts. Most of the time, if I've got a handout, guess what? I'm going to hand it out to you. So I'm not going to put that many on Blackboard, okay. PowerPoint shows. I don't have them yet, but I'm going to put them there. But guess what? They're going to be there two ways. Under content, under the PowerPoint, each chapter, that's going to be static. You can look at it ahead of time, you can read it ahead of time, you can print it ahead of time, whatever you want to do. But then, when we get to class, and I pull it up and I'm going to teach from Blackboard, it'll be there again on YouTube. And that way, you'll be hearing me talk about it and write on it and stuff like that too. So you'll have Blackboard or PowerPoint shows there two places. Once under PowerPoint and once under YouTube, okay? In the future, okay? These will be out, they're not out there yet, but I'll get them there. Activities, sometimes they post activities, the school does. I don't really post that many. Now, when you're in Physical Science 111, we went on a couple field trips, so I posted stuff on that, but we don't have that on this one, okay? Assignments, I already have one assignment out there, and that is the research paper assignment, and we'll talk about that a little bit later. So that is posted on Blackboard. Most of the others, if there is an assignment, I will be describing it and talking about it on YouTube. So you can listen to YouTube and find out what it is there. But I don't type it out. You got to do this. Okay. Announcements, again, most of those are from the school. And if they're there, they're there. Grades, I will put your grades. I'll try to, as soon as you get things in, like if you turn something in on a Tuesday, it might be Wednesday before I get it graded, or turn it in on Thursday. Probably I'll get it graded by Friday. Usually I use Fridays as a catch-up day, so hopefully, knock on wood, all of your grades will be out there by Friday afternoon. Hopefully, if you don't turn something in on Tuesday, I'll have it out there sometime Wednesday afternoon, because I'm in class all morning and half of the afternoon. But I'll try to get things out, but I try to get everything done by Friday. Now, if I'm having a treatment, I take all my stuff, I take my computer, and I work on stuff the whole time I'm there until they give me the Benadryl, okay? Once they give me Benadryl, I've got 15 minutes of lucid, and then I'm asleep, hopefully, okay? And I sleep most of the rest of the time. That's part of the stuff they do. Okay, so I'll try to get grades out at least by the end of the week, hopefully by the next day. I do not like the next sentence. Failure to use Blackboard could severely damage your ability to pass the course. It's such a negative sentence, isn't it? If I were writing this and they don't let me change it, I would say the proper use of Blackboard could greatly enhance your ability to do well in the course. It's a lot more positive, but I think it's closer to reality. Now, they have this one in there, see schedule book. We haven't had a schedule book in years, and yet they haven't changed it. So if you need to know anything about Blackboard, I saw this, okay, I'll be glad to help, or probably other students in the class will certainly know better than I, and we'll get you help, okay? We'll do whatever we can, okay? I do not like this next sentence. Students should always check the Blackboard announcement page prior to coming to class. Why would that sentence be in there? Any guesses? Say again? In case your class is canceled, okay? And guess what, team? I try not to cancel class. Did I? I try. I can't say I'll never, but unless something major happens, I'm going to try to be here. I'll try to be on time, and we're going to have class. And as he was asking, he wants that class for the full 5 hours. No, I mean 4 hours and a half. And I'm going to try my best to fulfill your expectations on that. Okay? So I don't like what that's implying, but never mind. I can live with it. Okay. Here are student learning outcomes for this course. Students will describe the nature of science, identify quantifying properties, use measurement systems, calculate densities, identify laws, principles, models, and theories. What we've just described is Chapter 1. If you got a book and you go to it, you'll see those are the topics in Chapter 1. What is science? Objects and properties, quantifying, measurement systems. That's what we're talking about in Chapter 1. Like I said, probably the most math you'll have the whole term will be in that there. Measurement systems and densities and things like that. Chapter 2, or student learning outcome number 2. Students will solve problems using the basic principles of motion. Guess what? Chapter 2, motion. Okay? Students will solve problems using the basic principles of energy. Anyone make a guess? Chapter 3 is energy. You got it. Number 4. Students will solve problems using the basic principles of heat and temperature. Chapter 4, heat and temperature. You got it. You're going to miss the next one. Okay. Students will solve problems using the basic principles of electricity. It should be electricity and magnetism. Guess what? That's Chapter 6. We skipped Chapter 5. Chapter 5 is wave motion and sound. And when I've taught the course before, we don't have time to cover everything, and I thought electricity and magnetism more important for most of you probably than wave motions and sound. So we skip 5 and go to 6. Okay? Students will solve problems using the basic principles of chemistry. There we skip Chapter 7, which is light, and go to Chapter 8, which is atoms and the periodic principles. Okay? So that's our chemistry. 5 chapters basically, well, 1 chapter on science in general, 4 chapters on physics, 1 chapter on chemistry. Now these are long chapters. Motion, that's a long chapter. Energy is a long chapter. Heat and temperature is a long chapter. Electricity and magnetism is a long chapter. The first chapter is fairly short. So it's going to take multiple class times to hit each one of those, and multiple labs in 2 also. Now, students will also write a library or internet-based research paper. You get to choose your topic. Please get it in. We'll talk about that next. Okay? Next. Students will conduct laboratory experiments and write up the results. I'll give you the lab sheets you need. I'll be in the lab with you. I'll explain and answer any questions you have. We'll do that. It may not be every class, but most of the classes we will have a lab. So, how do we go do this? Exactly like I was saying before, the competencies guide sheet, Chapter 1, you'll have 1 lab assignment, and I'll say this too. It's going to be the longest lab, most computations, probably take the longest to do, but it's all doable, not bad. And the test, and again, that one will have probably more math on it. It's not full of math, but it'll have more math than most of the rest of them. Chapter 2 will have multiple lab assignments and 1 test at the end. Lab 3, multiple lab assignments and 1 test at the end. Chapter 4, multiple lab assignments, 1 test at the end. Chapter 6, multiple lab assignments and 1 test at the end. Chapter 8, 1 lab assignment and 1 test. And then your research paper you can turn in any time between now and the last day of class. Not the last day of the term, but the last day of class. And then the comprehensive final exam will be that'll be the final exam day. And we'll talk about that in just a minute too. Okay, whoa. Evaluation and assessment. The following list is a breakdown of how each student will be evaluated for the final grade calculations at the end of the term. The research paper is required for the class. Required for the class. Not optional. not droppable, okay? It will count as a test score that cannot be dropped, okay? Research paper can't be dropped. Chapter tests will be given at the end of each chapter. Remember, every chapter had a chapter test. The lowest one of those may be dropped if it helps your grade, okay? Now, why do you say, how could it not help my grade to drop the lowest chapter test? Well, here's how. What if you file up your labs like crazy? You might need all the points you can get on the test to help bring those up. Or even worse, what if you don't turn in your research paper? A 0 there is going to take every test it can get to bring that up, okay? So I only do things that will help your grade. Just don't fail to turn in your paper or don't do your labs. Get them done, okay? There will be at least one laboratory assignment for each chapter. In fact, most of the chapters, multiple lab assignments. The lowest lab assignment may be dropped if that helps your grade. Again, I don't drop something if it hurts your grade, only if it helps. So if you, most of the time, if you have a low one, I'll drop it, okay? Or you can miss one. A lab grade will be average from the remaining lab assignments. So here's how I do the lab assignments. And Nickel, I hope maybe remembers this. Every lab assignment is 25 points. Every one is 25 points, okay? And then the lab average will count as 25% of your final grade. Now, where did that come from? If you remember back on page 1, 3 theory credit hours, 1 lab credit hour. So 1/4 of your credit hours is from the lab, so I figure 1/4 of your grade should be from the lab. The lab, like I said, we'll be doing as a group. You'll be in groups, most of the time. And I'll be there. You should do well on the labs. Here's where you won't do well on the labs. You don't show up for a lab or you don't turn in a lab, you don't do well on the lab. So please, it's 25% of your grade. Without a good grade on your lab, the maximum score you can have is a 75, right? So do the labs. So the lab average will count as 25%. And since I grade each lab on the basis of 25 points, whatever your lab average is, that part gets added to the rest of it. And here's what we'll do. The average of your paper, the remaining test scores, and the comprehensive final exam that cannot be dropped, that will count as the remaining 75% of your grade. So average all those things together, the paper, your, say, 5 tests, and the final exam, and take that average, take 75% of that, add your lab average to it, that gives you your possible 100 points. And I don't know, Nick, if you remember, what did you count helped your grade the most? Was it the lab, the test, or the
test?
Yeah, the test carries 75%.
And paper.
And the paper, yeah, that does too. So you can really do well by turning in those labs. That's 25 points. You either got it or you don't, or you got some portion of it. So don't fail to do the labs, and don't miss a lab. And if you miss a lab, make up that lab. Okay. Remember, though, the paper and the comprehensive final cannot be dropped. Okay. Comprehensive final is how we measure your overall understanding of the course. You remember anything about the final? Probably not. It's probably going to be one of the easiest tests you have. Okay? It's going to be matching. The others are going to be mostly multiple choice with a few calculations thrown in and around. First test, a few more calculations. Most other tests, 1 or 2 questions on calculations. The rest multiple choice. Your final, though, is matching. You should all do well on the final. You should all do well on your quizzes. On your labs. And there's no reason for you not to do well on your paper. Okay, so stand by. So anyway, here's, once we do those averages, if your average is in the 90s, you get an A, 80s a B, 70s a C's, and don't go here. Okay, no reason for you to get down there. This is a course that you should be able to do fairly well in. Okay, students are expected to attend all classes through registers, especially on these mini-term courses. Man, 1 class is a week's worth of material in a regular term. So don't miss it if you can help it. Students who are unable to attend class regularly, regardless of the reason or circumstance. I mean, people come and say, well, but it was an excused absence. An absence is an absence. You're not here, you're not going to get the material. If you don't get the material, you're not going to do well on the test. I can't help it. It's just there. Now, I've recorded everything I can. That helps as much as possible. Get your stuff in. Do the best you can. But if you can't come regularly and you're going to miss a lot of classes, you decide whether withdrawal is a better option for you or not. Now, some of you can hardly afford that because are y'all graduating in the spring? So, yeah. Yeah, but the automotive, y'all mostly are, right? You're in your second year. Yeah, so, yeah. So, but that's a better option than making a D or an F, okay? Now, withdrawal, guess what? Doesn't hurt you academically. A D or an F, they hurt you academically. A withdrawal does not. It may hurt if you're on a limited time, like y'all are, or it may also hurt if you're on financial aid of some nature. Because generally financial aid will pay for you to retake a class once, but not twice. So if you made a D or an F in a certain class once, you can retake it. But if you withdraw then after that, you can't, they won't pay for it the third time. They'll pay for the second, but not the third. So that's the only thing. If you are on financial aid, you need to beware of that. Now, none of you, I don't think, are in nursing or allied health, so you don't have to pay attention to that. Makeup work. Now, laboratory assignments are generally due 1 week after we do them. After we complete the lab, you've got a whole week to get them done. Most of the labs, frankly, we'll do in class, so you can probably turn them in that day. I encourage you to do that. But if you want to take them home and write them up or make some, check your answers, whatever, that's fine. But try to get them back in a week because I want to get them back to the rest of the students after that week. But if you haven't turned it in, I can't give anyone else's back. Okay, so please get those in within a week. If you miss a lab, try to get with me, try to get with a student, another student, get the data from another student, and let them know you're not going to be here, something so you can make up that lab and get it in. A partial lab is better than no lab. 15 points are better than 0 points, okay? So do the best you can. And we got a lot of labs, so those are averaged out. The zeros are hard to average out. So try to get that done. Now, if you have to miss a test, please try to get that made up in a week. Now, I've already told you my office hours are limited because I'm teaching 6 academic courses in this one, which almost counts like 2, okay, mini-term course. So, and 2 of my classes, this is a 4-hour course. 2 of the calculus classes I'm teaching are 4-hour courses. So, and then linear algebra, differential equations, pre-calculus algebra, and intermediate algebra. So, I mean, class most of the time only have very little office hours. But try to get me during my office hours, and we can make up the tests or the labs. Okay? Now, today I was late getting here. I apologize for that. It wasn't very late, but a little bit. I'll try to be here on time, and I'll try to get you out on time. Now, if we have a test or a lab at the end, you may actually get out a little early. I can't help that, but okay. Now, you've probably seen this in every syllabus you've seen since you've been here, statements on discrimination and harassment, okay? Let me summarize it for you. We don't tolerate it, we don't condone it, we deal with it if we hear about it, and we're fair but quick on it, okay? And I've been here, this is, I think, my 19th year of teaching. Now, the first few were at Western State Technical College on this campus, then we merged with Lawson, and frankly, I've seen very little, if any, what I would classify as discrimination or harassment. I'm not saying it hasn't happened, but I sure haven't seen it. I saw, there was one time, this doesn't really fit there, but it was one of my first couple of years teaching. And I apologize for this, but he was a kid in the automotive program. He didn't want to be here. I think his parents were making him come to school, and he was just killing time. And one day at lunch, he just decided to walk across the cars in the parking lot. Somebody saw that, they yanked him down. He was out of here, I think, in 15 minutes. I didn't even know it had happened until I called the roll the next day. And they said, oh, no, he's not here anymore. And they explained why. And I think even his classmates were said, good riddance, you know. So that's the closest, and that would be discrimination or harassment. But that's basically the timing it takes. If we see it, sense it, or think it's happening, we try to deal with it as quickly as possible. Okay? Now, on the other hand, if you see or sense or even have a suspicion that something is happening, not necessarily to you, certainly to you, but to anybody else, please let us know so that we can do something before it escalates into something far worse. Okay? So, notice here, will not be tolerated. Takes it seriously. It is never tolerated. You get the point? We try to deal with it. Okay. Now, you probably also have seen this on every syllabus you've seen since you've been here at the college. Americans with disabilities. Ooh, yuck. Okay. I have, I think so far, at least 2 students have given me something this term. And look, if you have any, as I've already told you, I'm hard of hearing, okay? That's mostly from being old, I think. But I was also in the Navy. I had the hearing loss when I was in there. Probably hereditary because I had some aunts and uncles who couldn't hear well. So, you know, several things. So I sort of am sensitive toward, you know, this is pretty minor, but, you know, disability. If you have anything, bring your documentation to either of the ADA rep, that's Dr. Renee Herndon, on this campus, and I've got to change that name. I forgot she has moved on, and there's a new person there. I can't remember her name. She's on the Birmingham campus. I'll get that corrected in the syllabus. Okay? Bring the documentation. You may have already had it. Just get it to her, this Dr. Herndon or somebody, and we'll follow it. If you don't think you're given a fair shake, we'll help you write us up. Okay? I mean, we're that serious about it. Let us know. We'll let you know what options you have for following it up. Now, they say course calendar here, but that's basically the academic calendar. It's out there on the website. Okay, so I didn't reproduce it here. You can see everything that's going on there. I can't think of anything big that's happening that will influence the course. It is a sort of bad news. I'll let you know this later on too. I guess you've heard the week of Thanksgiving, the entire week, no classes. I'm sorry. Sorry about that. Yes, because we have professional meetings Monday and Tuesday, and Wednesday's a day off. Thursday or Friday are state holidays. So sorry about that, folks. Get over it. Yes, ma'am. Oh, okay. Goodness gracious. Let me see if it's here. This is Math 112, right? I don't think I have it. I think it's down in my office. Yeah. Let me, let's take a pause for just a minute. I've got to go make a...
So on Thursday, class starts at 5:45.
No. Both days it's 3:15 to 5:45. Class 5:45 to 7:45 lab. Both days. Yeah. Okay. And the projector will come on in just a minute. But basically, any questions about Americans with Disabilities? If you have one, any nature, all those letters, AD, you know, whatever, any of those, get the documentation to Dr. Herndon. They'll let us know. One student has extra time on tests, one has a quiet room or something. I mean, whatever it takes. Calculators, whatever. We'll try to deal with it. I had a student in a physics class, actually, many years ago, who had a brain tumor, and they had several surgeries, but one of the surgeries, or the tumor one, affected his hearing, so he was basically legally deaf. He could hear something. He had his tape recorder right up in the corner of my desk. This is before we had, screencast-o-matic integrity, and he would take that home and crank it up as loud as he wanted to, so he could, whatever it takes, we'll try to do. Okay? Oh, I was talking about the course calendar. It's all on the website, Lawson State webpage. You can see academic calendar. You can see all the dates there. Okay? And I think the last thing here is the student acknowledgement form. Now, it's out there on Blackboard now. I've got to get that one name corrected, but that's not going to change much. Any questions about the syllabus? Okay. If you will, go to the Blackboard. You can either print this last page, sign it, and bring it in, or you can pull it off and email it to me. Either one you want to do. That you understand the syllabus and you've had all your questions answered. Any? All right, good deal. And if you have any, once you go back and review it, ask. Please ask. Never object to questions. Okay? So let's get through that. I've got to check on that woman's name. I know it, I just can't pull it up right now. I'll get that done. Okay. Let's go to the one that is in charge of this ADA on the Birmingham campus. Ms. Suggs, I think, got a job at UAB or somewhere, so she's no longer with us. Some other lady is in her place. I can't remember her name. Okay, the research paper. These are general instructions. You get to choose your topic. I'm not going to assign you a topic. You get to choose. It can be a person. It can be a theory, a phenomenon, an application. I really like to hear the applications. Any other subtopic about which you have an interest. Okay? Let me give you just a couple of examples. Okay. Now, I apologize to the other of you because about half the class, I think, are automotive students, right? Okay. Just on the applications, now one of these, I'll hear some boo hisses, I think, on, but one year, this is several years ago, one of my automotive students wrote on, I found this, it wasn't a great paper, but I found it an incredibly good topic. He wrote on the physics of the Wankel engine. Y'all know what the Wankel engine is? The rotary engine of the Mazda? He wrote on the physics of that, and I thought, a great choice, okay? And it doesn't have to be automotive, if that's your interest. Okay. Now, I'm not saying right on that, but I mean, there's just a ton of possible applications of physics and chemistry that might be applicable. Now, another student, and this was more recent, maybe just a few years ago, and it was a Ford student, I think, if I remember him right, wrote on the physics of the Ford EcoBoost system. Okay, sorry about that, but anyway, so if you have something that is really of interest to you, and it doesn't have to be in here. I mean, I've had people write on the physics of the black hole or something like that. I mean, if you're interested in astronomy or interested in anything, or in your field of study, I don't know what the rest of you are, but if there's something in your field of study that has applications for physics and chemistry, you can write on that. Or any person, theory, phenomenon. You choose your topic. Now, here's another option. It can be an internet application or demonstration or YouTube video or something like that that you find useful to the class. I've had a student one time find, and this was in the other Physical Science 111, on the Hubble telescope, he found this series of just incredible pictures that the Hubble telescope had done, and he, I don't think he wrote a paper, he just sent those to me. But if he had been interested and wanted to, he could have done that. Others, like if we're talking about conservation of energy, which we will, or electricity and magnetism, or heat and temperature, if you find something that you find is just incredibly enlightening about thermodynamics or something like that, and you want to write on that, or you want to pull that demonstration, YouTube video application, you can send it to me first and see if it qualifies, and then if it's really good, then I'll say, hey, I'll go on that. Now, you still have to write a paper. Tell me what you liked about that, what you found that it explained better than the book did, or if possible, better than I did. No, I mean, that's fine. Quite possible. Okay, or what you wish it had gone further in. Like I had one person, I don't know if y'all know what a Van de Graaff generator is. Okay, it's the thing they use in electrostatics. You may have seen it, it's a big bulb, someone stands on an insulating thing, put their hands on it, the thing moves and the hair stands up. Okay, someone did what was that? Mythbuster maybe? Or something like that. And someone showed how they built a Van de Graaff generator and the problems they had and stuff. So they found that really interesting. This may have been a physics class, not physical science, but they wrote on that. What they found interesting, what they learned from it, what they wish they had gone further, that kind of thing. Okay? So it can be an internet application or it can be a standard research paper. Either one you want to do. Okay? Now what I'd like you to do either today or next week, write on a piece of paper your name. That's pretty easy, right? Okay? And if you have decided a research topic, okay? So start thinking about it now. There's a motive to my madness here. I want you thinking about this early, getting to it, start looking for information, and start the process, okay? I'll tell you why in just a minute. So write that. Now, one piece of paper and just your name and the research topic, that's a lot of wasted paper. So if you want to do this, this is completely nothing to do with the research paper. But I'll just tell you, this happens not very frequently, but it does happen, that I'll get a panicked phone call from someone in admissions or the front desk or something, always to do here at the school, never to anyone outside the school, and say, this is so's in your physical science class, we need to get in touch with them. Do you have a good number? The one in the system is not working or it's been disconnected or something like that. So if you want to give me, when you're giving me this other on this piece of paper, your very best phone number, you can do that. I'm not going to give it to anybody. At the end of the class, that thing's going to be shredded and never seen again. So you can do that. Or if your very best phone number happens to be your cell phone, and there's a chance you could have left it at home or run over it by a truck, the battery died, the service changed or something like that, and you want to give me a good backup number like Mama's landline or something like that, that would be fine too. Or if you might be working when someone might be looking for you, which might be very likely for some of you, and you want to give me a work number, if it's okay for you to receive a phone call at work, you can give me that number. But you can give me 0 numbers, 1, 2, 3. I can't think of any reason I need more than 3 numbers. I don't need any of them, but that I might need that. So you can also give me those phone numbers if you wish. All I really need is your name and the topic. Okay? Now, you'll need to find at least 1, but 2 or more or better, outside sources for your paper. This book has a lot of good ideas in it. You may see something in here and say, yes, I'd like to write about this. This can be the source of the idea, but it can't be a source for your paper. You need to get out of the book, out of the class, either into the library or onto the internet. Okay, now be very careful about the internet. Okay, I tell my classes probably in my lifetime, which is a lot longer than yours, okay, probably the most incredible thing that's been created during my lifetime was the internet. Because I think in 1951, I don't think it existed, or if it did, it was in very rudimentary forms. And since that time, whenever it did come into place, it's just incredible. I mean, you can find anything out there. So, 2 problems with it, though. At least 2. These are just 2 major problems. At least, and probably far more than half of what's out there is total garbage and not worth your time and my time or anyone's time. The second problem is sometimes we don't know which half. So be very careful about the internet, okay? Make sure it is, and this is, I'm jumping a little bit ahead, the source can be anything from a book, a journal, an article, a newspaper, a magazine, any such material that you could find in the library, or any, and this is what I was talking about, legitimate source found on the internet. If you have doubts about its legitimacy, run it by me. Or run it by somebody who knows, like a librarian or somebody, and see if it looks like it's legitimate. If it is, fantastic, go for it. There's a lot of hoaxes out there, and there's a lot of garbage out there, so don't get tricked into that. But the textbook is not an outside source. It can give you ideas, but it can't be your source. Now, just about every chapter we have is going to have a blurb on some person And that person you may choose to write on, but you can't use the material in the blurb. You have to get outside the book to find it. Okay? Now, your paper must be at least one word process page of text. Now, what do I mean by that? Okay. This is a word process page, and this isn't one complete page. Now, I'll get to it later. A lot of you are going to use some format you either learned in English class or had in high school or something. And quite often they'll have, you don't have to, but they'll have the header at the top and something here and there, and somewhere down the page you'll finally get to do a title. You'll triple space and maybe start a paragraph here. Okay? Now, one page of text would start here, go to the bottom of this page, then go back to the top of the next page, and has to come at least that far on the second page to be one page of text. Because I don't want all header, all margins, and everything else and just have a little bit of text. That's not a page of text. Okay? So, now you get to double space. This is single space, so you get to double space. In fact, I prefer it. I really require it, okay? And I want 12 pitch and 12-point font, whatever they call that. No 26 points if 4 words fill the page and you say I'm through. That's not going to work, okay? So have it standard. The font you use is completely up to you as long as I can read it. I don't read hieroglyphics. I don't read Greek or Old English. Keep it something that is good readable. Times New Roman, that most things default. This is Arial, that's fine. Courier is fine. There are tons and tons and tons of great fonts out there. Make sure it's something I can read. Nothing curly-cued and stuff that I can't make out what letters they are. Okay? Try to keep the paper less than 2 pages. So shoot for 1 to 2 pages of paper. Now, if it's too short, you're going to lose points. I don't take off points for it being too long. If you go 2.5, 3 pages, if you just can't stop, you're so fired up about this subject, I don't want to squelch your enthusiasm. Please, that's fine. I don't mind reading. A good paper, I enjoy reading, okay? But don't make this mistake. Don't mistake quantity for quality. Say, hey, I really don't know what I'm talking about, so I'm going to say a lot more and get impressed with the mud out of them, right? That's not going to work. Because here's how I grade your papers. When you turn it in to me, it's a 100-point paper until I start reading it. And I can hear you right now saying, don't read it, don't read it. No, now I'm going to read it, okay? And as I go, if I find errors, whatever kind of errors, you start losing points. So if you turn me in a sloppy paper, but make it 5 pages long to impress me with its length, but it's sloppy and has a lot of errors in it, guess what? You're losing more and more points as you go. You turn me in a good paper, even a 7-page paper. If it's a good paper, well written, stuff like this, it's going to get a good score, okay? Or a 1.5 pages or 2 pages is going to get a good score, okay? So please don't substitute quantity for quality. Give me quality, okay? Shoot for a page or 2, but if you go over it, don't sweat it. It's fine. All right. You can use any format you choose. I know most English classes teach MLA, Modern Language Association format. Fine with me, I don't care. A lot of scientific organizations have used APA, which is American Psychological Association format. I don't know why, they just came up with a great format and everybody liked it, so lots of people use it. I'm a member of a few professional organizations. Some of them have their own format, you know. Pick a format, stay with it, whatever it is, okay? So, for instance, if you start in blocking paragraphs like I did, block all your paragraphs. Don't have this one blocked, that one, then suddenly this one's indented, and this one's indented a different amount. That's not being consistent. What I'm guessing is happening is you're reading sources, and some of them indent, and some don't, and you're just doing what they do. You pick your format and stay with it, okay? Spelling, grammar, sentence structure, all those things that lose you points in English class, they'll still lose you points here too, okay? They are important because guess what? You're producing a product, okay? Say you're writing up an estimate for a customer. If that's full of spelling errors and stuff, that customer is not going to be impressed and probably going to say, you know, down the road, I think they do a better job of this. I can't figure out what they're saying here, you know. So, you know, all that's important stuff, not just in this class, in life, okay? So, guess what? I think just about all of your word processing packages have spell check on them these days, don't they? Use it! I've had so many papers come in, usually at the end of the term, when people have waited till the very last moment to do it and just zapped something down and turned it in, and I can tell they didn't use spell check. Or they sure didn't use grammar check. Most word processing packages, I think, have grammar check. And also use good proofreading. Here is the best thing that I found for good proofreading. I remember a high school English teacher I had gave this example. I've never heard anything better. She said, when you work on a big paper like this isn't a big paper. She was talking about a 5-paragraph essay or a research paper or something. This is a research paper. It's not that big. But she said the best thing to do is get it done and let it sit. That's what she called it, let it rest. Maybe for over a weekend or maybe a week if you have that luxury. And then she said, pick it up with fresh eyes and read it as if you've let it sit, you forgot what you were saying. You know, pick it up. And if you're reading it, say, wait a minute, what do I mean by that? Guess what? I'm going to be saying the same thing. So that's a really good proofreading technique. My wife is a researcher at UAB, and she was working on a grant the last couple of weeks and just been horrendous hours. And she said the other day, she said, I was going to send this to one of her colleagues for them to review, which is a good idea to do, you know. So she said, and I got to reading something, I thought, what in the world was I meaning there? So she said, I know it wasn't clear because I couldn't figure out what. It made sense when I was typing it, and guess what? This is not good proofreading. Type, 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 read. Type, 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 read. Because guess what? You know what you're trying to say, and when you read it, it's going to say that to you. Even though you left out 3 words, you know, you're going to put them in because you knew that's what you mean. So let it sit, do good proofreading, okay? Now, content also matters. If you write on energy, I know a little bit about energy, and if you make some really glaring errors, you know, I'm probably going to pick them up. I've also, like, if you're writing on a person, I actually had this happen. I don't know the exact person or the exact dates, but they gave they said thus and so, gave the name, and then they put in parentheses the year of his birth and the year of his death. And then over on page 2, they had him dying in a different year, you know, than he did on page 1. I said it wasn't that long of a paper, so I don't think it had that big a difference, okay? So I'll pick up most content matters like that too. I've had people write on theories that they state the theory, I know, totally wrong, you know. I know what you're meaning, but that's not it, you know, that's not there, okay? So please, content also matters. Now, as I've already said, the paper is due by the last day of class. That's not the last day of the term, it's the last day of class. Before your final exam. It's not due on final exam day. I've got enough to grade on that day. Get it into me before that, okay? If it's after that last day of class, you're losing points, okay? Now, I highly recommend start working. That's why I want you to get the topic now, okay? You can change your topic 15 times if you have time to do that, but I want you to start thinking about it now. You'll never have more time to work on the paper than you do right now, this coming weekend, you know, whenever. This is the time to get started on it. Start finding your sources, look them up, start writing, start putting it together, let it sit, read it later, you know, start on it now. Because I bet you, especially if you're if only doing mini-term courses, you don't have many other projects due right now, do you? Quizzes, tests, presentations. Guess what? At the end of the term, you could have all of those and more, okay? Final exams coming out your ears, you know, lab dues, you know, other things. So please get started early. Don't put it off, okay? Now, that's the stick. Here's the carrot, okay? If you submit your paper during this month, the month of October, you get 2 bonus points added to your grade. Whatever your grade is, I add 2 points to it. If you turn it in the month of November, you get 1 bonus point. Turn it in the month of December, you just get your score, whatever you score. You turn it in after the last day of class, you start losing points, okay? So please, get it done as soon as you can. Now, here's one other thing I require that most of your English teachers or others probably don't. When you submit your paper, attach a single page from one of your sources. Let's say you had 3 sources. Pick a source, any source, I don't care, and pick a page from that source. And if it's a source in the library, take that book or the magazine or journal or newspaper over to the copier, copy me 1 page. If it's something off the internet, then print a single page from the internet article or wherever you got it. Now, if it was one of those things that you got off, that you're reporting on a YouTube video or a website or something that you got interest, it's hard to print something off of there. Then you just send me the link, okay? You're going to have to send that to me anyway, so send me the link, okay? Now, any questions about the research paper? Okay. Again, this is out there on Blackboard already. It will be on Blackboard in the YouTube video that comes from today's class. Refer to that when you're writing the paper. I've had so many papers coming at the end of the term with no page from an outside source, or done something else that I clearly stated, please don't do this, or did something. Okay, you got the idea. Any questions? All right. Yes. Oh, okay. All right, through with that one. Now, let's do, I think we got one more. This is my locator card. This shouldn't take long to do. Ha! I asked my work study student to do this. He forgot to change that to second mini-term. I'll get it changed later. Fall term, second mini-term, I'll get this changed on Blackboard too. There's my name again. There's a phone number again. Remember, call me during office hours. Don't call when I'm not on campus or when I'm in class. I may not hear it. Email address, I'll try to do a little bit better about getting there. I am in the math department, though. This is physical science. I'm on campus every day, every morning, usually by 7:45. Now, a few days, like this morning, I may have been 7:46 because on the interstate, there was a big, slow truck in the left-hand lane and one that was about the same speed in the right-hand lane, and they kept doing this, and everybody was backed up behind them. And, things like that happen. And this morning when I was leaving home, driving through the neighborhood, a street was closed, and I had to find a detour that was not an easy detour and drive around to get it. I never could figure out why they had the road closed. So sometimes I might be a little later. Most of the time I'm earlier than 7:45. In the office then, that's a good time to catch me, 7:45 to 8 o'clock. Have 8 o'clock classes 4 days a week on the Birmingham campus Friday, okay? Hour and 15 minutes, followed by a 9:30 class 4 days a week. These are calculus classes. This one is, that's a calculus class. It's a longer class. It's a 4-hour class. These are 3-hour classes. This one I have 3 classes in a row. Here I have lunch in between, another calculus class after lunch. Okay, so not many office hours there. My lunch is, I'm in the office then, so you can see me then. Friday, the whole time is in the office, except if I'm in meetings or off campus if I'm having a treatment. Now here's the sad news. Now that, I think we'll see it all. Okay, he didn't quite do it right, but he came close. I'll have to get this cleaned up a little bit. Because I'm here until 8 o'clock on Tuesday and Thursday, technically I'll leave at 2 o'clock on Monday, Wednesday. I don't. I will be here after 2 o'clock. I can't say how long, but usually about 4 to 5:15, 4:45 to 5:15, I usually am here. Now, if I have to leave early, I'm not supposed to be here any later than 2, but I will be. So you can catch me then, and on Tuesday and Thursday, the best time is between 1:15 and 3:15. I'm in lunch before that, but I'm in my office. You can catch me there too. So if you have to make up a test, find out what we did in the lab, something like that, these are the times. That's the time on Monday, Wednesday. Sometime after 2 will be fine too. That's the best time on Tuesday, Thursday, and just about any time Friday morning when I'm on campus. Okay, any questions? Okay. That just shows my office hours in gory detail. Okay, I've got to make a few changes there. I'll put the lab time in as well, but he put first mini term, he didn't change that. All right, now there's a couple of other things we need to do before we start the actual physical science. Sorry this is taking too long. I run my out too much. There are a few things we have to be aware of, and you probably have heard this in other classes, but if not, you should have. There's 3 types of, say, emergency. Did you finish? All right, good, thank you. So I can mark out the do not finish? Okay. Okay. Okay, sorry about that. Okay, 3 things we have to be aware of. Now, this time of year, this isn't as common, but it could still happen. Weather emergency. Okay? If we happen to hear that siren go off, what do we do? What's the rule for weather emergencies? Say again? No, not quite. Okay. Say again? Okay. Okay, and where is that? Think of this, low interior. Okay? One of the worst things you could possibly do in a weather emergency is get in the car and try to beat it home. That is an awful thing to do. If you were around, what was it, 2011, April, there were so many places that a tornado actually almost followed 2059 from Tuscaloosa here. I mean, the damage was just all over the place. You did not want to be on the road when that was happening, okay, ever. Tornadoes target cars like trailers. They love to pick them up and throw them around. So don't try to beat it, okay? Go low, go interior. Now, where does it mean here? Now, this won't all be recorded, but hopefully you'll know this. You go out of this door here, take a left, you go down there, you'll see this half flight of stairs right there. That's still second floor down there, half flight of stairs, but just at the bottom of those stairs, take a left, okay? Go down one more flight. You're very close to the lowest part of this building, okay? It's that level where the library is, okay? So really, here's the other thing to think. You go low and interior. The other thing to look for is corners and close walls. Now, believe it or not, one of the safest places to be is probably in the restrooms there on the first floor, because the walls are close together, you got a lot of corners, and it's interior, no windows. The bad news about restrooms are it's probably not the greatest place to spend a couple of hours if it's a prolonged stay, okay? The other bad thing is if it really is a severe weather emergency, there's a good possibility we're going to lose power, right? And the bathrooms don't have emergency lighting. So again, probably not the most inviting place to spend 2 hours, but a very safe place. Now after that, just past the restroom, now there's a couple of steps there, so be very careful there. The next thing would be, right next to the restrooms down on the first floor, is a small office space that's the academic dean's office. Now usually it's locked up, but if she or the associate academic dean or anyone else happens to be in that space, again, it's a small space, closed walls, interior. If they invite you in, there's actually places to sit. Now again, there's no emergency lighting there, but at least it's a little more comfortable than the restroom. Not that the restroom doesn't have a couple places to sit, but they're still not all that comfortable. Okay, so never mind. All right. After that, the next room down is this is second floor. This is exactly what's on first, but it's pretty close. The next is room 160. Okay? Room 160 is that developmental math classroom. It's a pretty big room, probably about the size of this one, so it's not ideal, but it has several advantages over this one. It's not an external, it's an interior room. So that's an advantage. And if you stay near a wall, especially the back wall of that classroom, the side away from the hallway, there's soil on that side of it. There's no, that wall can hardly fall down, I think, okay? So it's pretty good. The corners are best. That's where the greatest strength of anything is a corner, but the walls are next best, okay? So especially the back walls. The side walls are still okay, even the wall to the hall, not the best, but it's still better than being external. After that, there's a couple of library rooms. The first was that computer room, you know. That was fairly close walls, smaller than the classroom, so that's not a bad space. The next one over is a, I call it the research room or the reserve room or whatever. It has the globes and the atlases and that kind of stuff. Usually not what you check out, but that's an interior room. Not bad. It's bigger than the computer room, but not bad. But really, probably the best is the hallway. The hallway doesn't have any corners, but it does have walls, and it does have emergency light. It's probably the only space down there that will. Do not go to the external rooms. So any further in the library, you're going to have windows. Don't go in those rooms. Don't go in the rooms on the outside. They are the dangerous places to be. So the place to go is down interior. Lowest level, interior. Okay. Other things to keep in mind. Right now, all of you look in pretty good shape. Okay? I can't say that no one's going to go on a weekend and go up skiing or doing something else and break a leg. Okay? I hope it doesn't happen. But if it does, I'm going to be hanging back and making sure you are able to get downstairs. I may get a couple more of you really able-bodied type people to help me, and we will get anyone who's in a wheelchair or on crutches or something like that and helping them get down. In one of my earlier classes today, have a student, I'm pretty sure she has cerebral palsy. She makes it really well, but you know, it's a struggle. I would be staying back with her if it happened during that class, making sure she gets downstairs safely in a safe place. So in other words, the odds are y'all are going to get down there before I will. I'll be, as my mother used to say, the cow's tail. I'll be the last thing down there. If that's the case, you hang tight. Don't go visit friends. Hang together until I get down there, because I have to call roll again. Okay? And once I get down there, if someone's missing, then someone's got to go looking for them. Either me or some emergency personnel or somebody has got to go trying to account for everybody. And if you're off visiting friends or taking a break or trying to make it home or something like that, someone's risking his or her life trying to find you, and we don't know. So stay together. I call roll. They'll let us know. Then after that, you can mingle around with friends if you want to. All right. Anything else on weather that you can think of? Another type of emergency. What would that be? That's something outside the building. What if there's something inside? We're right next to a fan room here. Now, just recently they replaced all the units in there, and that's why we don't have any control of temperature or anything. But hopefully everything's in hunky-dory shape. But you know, a bearing could go bad in there. And if that bearing overheats, then grease around it, you start having smoke and heat and all sorts of bad things happening. So we're talking fire or chemical or some sort of spill or something like that. What do we do then? Okay? This shows you what to do. In fact, it's all right here. We evacuate. This time we get out of the building, not in the building. Okay? And where do we go? All the procedures are here. The quick facts are right here. Evacuation, fire, hazardous materials. Here's the tornado and storm warning here that I just talked about. Okay? So power outage, what to do. Where we go, this is the overhead shot of where we are here. It's not a great shot. This is the A building, big old A building here, okay? Where they want us to go, we're back in this corner here. This corner here, okay? And where we go is here. This big parking lot that's between, I said it wrong. This is the A building. Okay, got it wrong. Sorry about that. There's the B building there. This is the A building. We're in this corner right here. Okay, where do we go? Down the stairs, half flight of stairs, down one complete flight, and then rather than going into the building, we get out of the building. We go out of this door right here. There's an exit here, the one that's right here, and we go out across this grassy area into this parking lot. Now, if it's a miserably hot day and you want some shade, you'll find some shade under some of these trees back here. But otherwise, we go to the parking lot. And again, we get at least 75 feet away from the building. Because if there's a fire or chemicals in the building, there could be an explosion. If there's an explosion, this glass is going to go flying that way. You don't want to be near the building. Get at least 75 feet away from the building. That parking lot will surely do it. And we stay together, again, because I'm going to be the last one, helping everybody, make sure everybody's out. And when we get out, then we're going to meet together. And I'm going to call roll, and if we're missing somebody, that means some emergency responders got to go in and look for you. And if you've wandered away somewhere, you're putting his or her life at risk. Now, I left something out there, pretty important. What if we're the first ones to see the smoke coming out of these vents? Or something explodes in a transformer out here, and we get a fire in this room. What's the first thing we're going to do? Second? Fire alarm. Very good. Where is the closest fire alarm to our room right here? Okay, you would think in the hallway. Okay. You weren't here before, were you? Okay, let me get your name on the roll. What is it?
David Carroll.
One more time.
David Carroll.
David Carroll.
Yeah.
Is what you go by?
Wayne.
Wayne? Okay. All right, good deal. Okay. Okay, we're just talking about fire safety, and I asked where the closest fire alarm is, and you said somewhere out in this hallway. Well, guess what, folks? These hallways you see here, second floor, these are all the old part of the building. This building was built back before fire alarms were required as part of the building code. So you can look on all these halls as far as you want to, you'll never see a fire alarm. Now, the good news is, this part in here is first floor, that's why it's not showing up here, because this is second floor elevation. But if you go down this half flight of stairs and through this corridor right here, you're on second floor here. When you go through here, you're on first floor. That's the new part of the building. That's the part where Student Financial Services, Records Office, Admissions, Student Development Services, Dean's Offices, that kind of stuff. They're all in here. That was built since I've been here. Because you do have it right, when you go through this corridor, right around the corner, there's your closest fire exit, your fire alarm. So someone has to go. And I'd suggest 2 people go, just in case someone slips or falls or something else. 2 people go and reach that fire alarm and let it be known. Then you proceed out of the building. What else do we need to do before we get out? The fire alarm will tell everybody here that there's a problem. But the best thing to do is dial campus security, campus police. Does anyone have that hardwired into your phone? Probably not. Okay? So if you can't contact, they used to have a phone back here in this office. All I had to do was pick it up and dial 1. That got me straight to campus police. They took it out, so there's not a phone there to use. I don't have a cell phone either, okay? So I couldn't call them. Where would you call if you can't get campus police? 911, okay? They'll be a little upset with us. They know before they do, but they get to hear the alarm, okay? And then on that, if you can call campus police, then tell them exactly where it is. Room 255, the fan room next door, or the ballast in the ceiling, or whatever. Let them know the best description of what the fire is, what kind it is, electrical, grease, whatever, so let them know. So that I left out before. We do that first, then we proceed out. Okay. Oh, except for this. What if it's, okay, your book just started in spontaneous combustion?
Oh, man.
Now, you're right. Now, what can we do about that?
Put some water on it.
Okay, actually better than water,
Get out.
because it's closer than water. Fire extinguisher. Where's the closest fire extinguisher? Anyone know?
In the motor. Right here.
About 5 feet from where I'm sitting, right there. Right there on this wall is the closest fire extinguisher. If the fire does start here, see that fire extinguisher, if it's electrical, it's fine for it. Water on electrical fire, never. Water on a grease fire, never. Okay? Fire extinguisher on any kind of fire, that's the way to go. So if it's in this room, y'all get doing that. Someone get me the fire extinguisher, or I'll get it, and we'll start working on that. I'm trying to help people out, especially if your book exploded. I might need to help you get out. I mean, I'm just kidding. Well, it may never be. Okay. So we do that kind of stuff first. We got to warn other people before we leave and say, hey, we're getting out of here. We don't care about, no, we don't do that. Okay. So there's 2. Weather emergency, internal emergency, as in fire or chemical or something like that. There's one other kind that we never even thought about before, but now it's reality. Bang, bang, active shooter. And this has happened on at least one community college that I know of, okay, not in the outside of Alabama. And unfortunately, we have to think about it. What if y'all hear, and guess what, I'm hard to hear it. You're going to hear it before I do. What if you hear something that sounds like shots? What do we do? Please don't, okay? Not when I'm here, okay? What do we do? What's the action that we take if we hear shots? Say again?
Take cover.
Okay, very good idea, okay? Now, here's what I will do. I can't lock this door from in here or even here. There's no buttons or anything else. I actually have to go outside. I've got a key, and I will lock the door. I'll come back inside and close this door, okay? So it's locked from the outside. Now, we still have the possibility they can get in from here. Now, this door does have a button that you can lock this door, but guess what? It locks from here, but not from there. Not a good idea. That locks us in, but it allows him to come in. This door has a deadbolt, but I don't have a key for it. So that's not a good. But this door over here, okay, it has buttons. And this door, this has a lock. So that's why, if I don't have a chance to get we can lock that one. We close this one. Why? Or you can see right through. Close this one so you can't see. Okay? We'll also close this one too while we're at it, but we won't lock it because it locks us out. But we get away from the windows. So your take cover is a great thing. Don't be standing here where he can see you. We want him to think this room is totally empty. So guess where we go? Right back in his lap. No, I mean, you go right back here because you got all this concrete block. That's hard to shoot through. He can't see, okay? And we all get here and we're very quiet. We're a nice, tight little family. We make no noise until we hear all school, okay? And that's what we do. And if y'all got a cell phone, 911. Or if you have the campus security phone, that's a good thing to do. Get that as one of the speed dials on your cell phone. I don't have a cell phone, so I'm the one person in Alabama that doesn't. Okay, so but you know, get that on there. Get campus police on your thing so you can call them if you ever need to. Okay, hopefully you'll never need to, but it's a good thing to have. and we stay very quiet back here. He can't see us. I say he, all of them so far I think have been he's. I know one was assisted by his wife or somebody, but I believe it was always. Okay. Hate to have to say that. Any questions on any of the safety issues? All right. Blah, 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 right? Never mind. Okay. Now, and let me ask or say this to you. You know, I call the roll because this has listed for class and lab, always every day at 5:45, I've got to call the roll again, okay, because they require us to here. So if that sneaks up on me, stop me. We got 30 minutes plus before I need to do that. Okay, enough of this, okay. Any questions on any of this stuff that we talked about? Okay, if not, then let's move on to physical science. Finally, okay. And again, for those who may have come in a little late, we're going to do, and by the way, okay, you got a book. Did you get it from the bookstore? Oh, good. So they have got some in.
Well, actually, got from a friend. So.
Oh, from a friend, okay. Yeah, the bookstore for some reason had only lab manuals, which I hadn't even ordered, and access cards that you could get ebooks. And I said, I didn't order those either. And I guess they made the choice or someone messed up the order. But anyway, I found this out last week. I told them about it. They said they have it overnighted to us. It should be here Monday. It wasn't here yesterday. I didn't have a chance to go check today. I've been in class just about all day today. So, but obviously they weren't. But they did have a few. Could you show yours again? A few, not many, of those that are really cheap. Those are only the chapters we're covering. So if you can find that, that's a pretty good cheap option. Otherwise, you can rent. Nick got his on Amazon, was it? And for like $6. Now you might not. Well, you got one for $6 too, didn't you? Or $6.21 or something like that. So you can get deals other places, or you can rent. But try to. So we're starting in chapter 1. We're doing chapters 1, 2, 3, 4, skipping 5. And it's skipped in that. It's not even in there. 6, skip 7, and 8. Now, that doesn't sound like a lot, but they're big chapters. And guess what? We only have 8 weeks. So it's going to be pushing getting everything covered. So we're starting in chapter 1, which is one of these sort of nebulous kind of sounding chapters, but I found the information in it is worth doing. Early on, I tried skipping this, but I found really the material in here we needed later on. So let's get started with chapter 1. Let me get the slideshow set up from the current slide. All right. Again, sort of a broad topic. What is science? Okay? Big topic. Core concept here. If you got your book, the core concept is usually on the title page of that chapter. And for some reason in my book, they have it in white type and yellow background, which is really hard to see, but it's usually there right about in the middle of the page. Science is a way of thinking about and understanding your environment. And if you think about it, that's a pretty good description of what science is. It's dealing with real world things, okay? And it's not just some abstract thing. It's your environment. Way of thinking about and understanding what's around you. Physics is the motion, energy, transfers, things like that. Chemistry, how things are put together, how things are built. And guess what? Those two really go hand in hand too. We're going to talk about some of the same stuff in both sections. So what is science? There's a few quick quips, you might say. The search for sense. Okay, that's pretty good. That's sort of understanding your environment. Finding orders in your surrounding. That's understanding your environment. And some people think of it as tools and rules. Probably not the best way to look, but it's still not too far off. It gives you the tools and the rules for understanding what's going on. Okay? And I guess there's a reason for this picture here. One reason is just why everybody's moving in the picture, so everybody is in motion. That's physics. Okay? Most of the folks are carrying things. That's physics. Now, some of these are carrying them in healthy ways, and some of them are carrying them in maybe not quite so healthy ways, okay? Because they could be putting extra stress. So guess what? Your body reacts to some of the choices you make on how you apply the physics of your everyday life. Now, everybody here, I bet you, has at some time that day eaten, and their body is doing biochemical changes to the food to give them the energy to do the motion they're doing. So there's chemistry involved, there's physics involved. You see the trees, that's chemistry going on in those. The architecture, there was physics going on in building that. Everything is involved, understanding your surroundings. Okay? Here's the overview of the whole chapter. Not the whole course, this is chapter. It's not quite half and half, a bit more here and not quite as much there. We're going to first talk about the quantitative description of science in general. Okay? Objects and properties, quantifying those properties, measurement systems for quantifying those properties, standard metric units, that's one of the standard measurement systems. We'll look at metric prefixes as we understand those standard metric units, and we'll do some understanding from those measurements. Okay? Now, included in that are a few things like ratios and things like this, ways that we use the data we collect. Then the last part of the chapter, to me, is a little more nebulous, but it does talk about the scientific method. We'll mention a couple of giants of science in there, so maybe people you'd be interested in writing on. There is a paper required in the course, okay? Explanations and investigations, what makes up the scientific method, how that differs from how things were done in the past. We'll look at laws and principles and how they compare with models and theories, okay? Just some of the nomenclature about how things are put together. I'll mention a few. Some of those may be of interest to you. Okay, that's the chapter. So let's look at the first, objects and properties. Objects, things you can see, things you can touch, things you can measure. Those are what we mean by objects, okay? Not predicate objects and things like this that they talk about in English. It's actual things. Now, properties are the qualities or attributes of those objects, okay? Let's take an object. How about this desk? What are some properties of that desk? Qualities or attributes of that desk?
Metal.
It's what?
Metal.
Okay, it has 4 legs, okay, that are supporting it. You can describe those legs. They look like they're metallic. I'm pretty sure they're hollow, okay? They're supporting it, so probably will hold a fair amount of weight, okay? Anything else? Lots of things. I mean, the top looks like a different material. Probably not wood, but a wood product, more than likely. This looks like a plastic product here, okay? It differs. You get in on this side, you can't get on that side. It has a tray. Oh, yeah, you can describe that desk. You talk about its color, its weight, its height, its width. Those are all properties of the object, right? Attributes, characteristics of that object. Now, here's a word, I think before I read this book, I'm not sure I'd ever seen the word before, but it makes sense. A reference, okay? That's not a reference, but a reference, okay? Those are things you refer to. If I were going to say, I want to measure the top of that desk, okay? What will I use to measure? Maybe I'll use this pencil, okay? This would be my reference. That would be 1 pencil, 2 pencils, 3 pencils, 4 pencils, about 4 pencils wide, okay? Rather dumb method. Hey, look at what he pulled out. He pulled out a standard reference, okay? A tape measure, okay? And there you could use something very standard. Your reference, though, is what you're referring to. A comparative properties that's familiar to others. Like if I say it's 4 pencils wide, well, you know, I've had little pencils before. I use them till they squeak, you know, I mean, tiny little things. Or I've seen some pretty good sized pencils. So that wouldn't be a very good comparative property, okay? Pencils. Inches off his measuring tape, that would be a good one. Everybody knows pretty much what an inch is. I bet you his measuring tape also had centimeters and millimeters on it. So you could use that. More of the world is familiar with that than is familiar with inches and feet, okay? Many more in the world. In fact, very few in the world, except us, use those others. So those are comparative properties and other more familiar. Now here's some really dumb examples. If that desk, like this one here, you say the seat is blue. Well, there's lots of different blues. This is not what I would call a sky blue. It's not quite a cobalt blue either. How would you describe it? You make a reference to it that people would understand or at least have a clue on. Okay? Lemon yellow. Well, I've seen some lemons that were more yellow than other lemons, so that's probably not too good. That's a problem we have. Language can be subjective, ambiguous, and sometimes even circular. Okay? Whereas his tape measure, that's fairly precise. You can find out exactly what an inch is, or a millimeter, or a centimeter, and then you have something far better. Better than how many pencil lengths, okay? Far better than that. So this is what we're meaning objects and properties. Okay. So we use some quantifying properties, okay? Measurements. They use these quantitative reference, which are called your units. Okay? Pencil's not a good unit. Okay? Lemon yellow, not a good unit for color. Okay? Sky blue, not a great unit for color either. So here's what we do. If we were using one of the reference, even if it was, just like I did, comparing the referent unit to the property being described. Okay, this desk. Okay, what are some length measurements I could use to measure this? I've mentioned a few. What length units would you say we should use for measuring the desk? Miles? How many miles long this desk is? No, that doesn't make a lot of sense because that's such a tiny little fraction of a mile. How about millimeters? Want to count how many millimeters that is? I don't particularly either. Micrometers even worse. A millimeter, by the way, is about the thickness of a dime. So if I was going to measure how many dimes it takes to go across the desk, I'm going to be here a while. Okay? Thickness is a dime. So you want to compare the reference unit to the property being described. So what would you use? Feet, that wouldn't be too bad. Or inches, yeah, those would be pretty good. Meters, you could, but I'd probably go with centimeters because that's a lot more reasonable. Now, how about if you're saying from here to Tuscaloosa, you want to use centimeters for that? Inches? Oh, miles or kilometers, either one. So you compare the referent unit to the property you're describing. If I'm measuring the length of the grassy area out there, let's stay away from millimeters, okay? Let's use something that makes more sense. Meters or yards, maybe, okay? Following a procedure specifying how that comparison is done. Now, if you saw me do my pencil thing, you notice that my thing was try to line up the pencil as close to the edge as I can. Now, what's the edge, okay? There's an edge right here, but then there's a place that's rounded here. What do I use? Do I use the rounded part of it? You have to define that, okay? That's going to introduce some error if you don't know it. And then I put my finger here and then move that and try to hit the same place every time. Okay, now maybe off the thickness of my fingernail there, if I was on this side and that side, that's not going to be a big error, okay? But it will be an error. You have to understand that. So you follow a procedure for specifying how the comparison is done. Now, if he was using his tape measure, my guess is that lip is going to catch the bulb part here. It's not going to be the thing here, okay? Because it has this little lip on it, okay? That's a smaller one than I was guessing, so you put that down there, and it's probably, it's going to catch most of that lip, okay? bring it over there, and then measure, okay? Now, what if I did like this? Is that a good measure? No, because it's not. So to try to get it about the same distance from the edge, front and back, is here. I don't want to get down here because here you're in the curvature. So you see, you have to describe the procedure you're using for your particular reference. Okay? Now, count how many standard units to describe the property. I said it was 4 pencil lengths, or a little give or take. Or I didn't see it was so many inches or so many centimeters. Those were the ones I saw on his tape measure. Okay? Or miles to Tuscaloosa, or kilometers to Tuscaloosa, or yards across the field out there, or meters across the field. Count how many of those standard units. Now, this is probably the most important thing on the slide. When you're measuring something, you're going to have a number, right? 4. For what? Second, those are pencil units. If I don't say pencil units, you don't even know what I'm talking about. If I said 4 or 25, am I talking inches or am I talking centimeters? You'd have to know what the size of the test was to say, oh, I think he's talking in centimeters, okay? Because that's not 25 inches or whatever, okay? So anytime you give me a measure on a test in the lab, be sure you include a number and a name for the reference unit. Inches, centimeters, seconds, meters, feet, yards, degrees Celsius, degrees Fahrenheit, whatever you give me. If you give me a number, be sure it has a unit. Now there is a story, I don't know the full details of this, but I have seen or heard about it several different times, and so I know it actually happened. Now maybe my knowledge of how it happened is wrong. But what do y'all know about the 60s? Anything particular?
I wasn't alive for
What's that? You weren't alive then?
Wasn't alive.
Okay, I was. Okay, rub it in here. Okay. But if you studied any history, what were some things going on in the 60s?
Woodstock.
Oh yeah, we should have figured you would know that, okay? There was a thing between, especially the Soviet Union, USSR, and the U.S., a certain race that was going on.
Space race.
A Cold War was going on in the space race, exactly. Who got the jump? The Soviet Union jumped out way ahead of us. Now, y'all know, this is completely beside the point, sort of why that happened or how that happened? What had happened before the Cold War? World War II. Who were some of the big honchos in World War II? Who was the antagonist in World War II? Hitler was the person. What country?
Germany.
What was Germany known for? Second? Hitler. Okay, I got it. Okay, that's what we call circular logic. Okay, right. Germany had some of the finest scientists out there. They were way ahead of us in rocketry. Does the name Werner von Braun ring a bell? Where from? Second?
Germany.
Okay, he came from Germany. He certainly did. Where did he wind up?
What was his name?
Werner von Braun. Huh?
Yeah, man.
Where did? I can't hear you.
In North America?
Yes, in North America. Did anyone know particularly?
For a time of bomb.
Huh?
For a time of bomb.
Okay, yeah, you're getting it. Mostly the rocketry that launched it. So, yeah, you're thinking Oppenheimer was big on the atomic bomb. But these are all German names, right? Where Werner von Braun wound up mostly was Huntsville, Alabama. The von Braun Center. The Space Center there. He was largely, okay. Now, when Germany fell, how was Germany divided? Anyone know that?
East and west.
Yes, there was East Germany and West Germany. Now, anyone know the basis of those? Actually, West Germany was 3/4 approximately of Germany, because the U.S. sort of got a piece, Britain got a piece, and France got a piece. think that's how it was split up. The fourth piece was Cold War, Soviet Union. Okay, that was in Eastern Germany. It was actually northeastern Germany. Well, when Germany fell, the Russians were coming, or the Soviets were coming in from the east, and the Allies were coming in from the west, and they were gobbling up, and really, they were almost as interested in getting those scientists as they were getting the land and defeating the army, because the scientists were going to be what determined. Russia got a whole, or USSR got a whole bunch of scientists. We got all we could grab, von Braun and Oppenheimer and those. I think Einstein had already come to the U.S. because he was part Jewish. He had to get out of Germany. Thank you, Hitler. Okay, no, I'm just kidding. But it was a race to get the scientists, and the Soviets put their scientists to work really quickly in developing rocketry to get into space. Anyone remember what the really bad rockets the Germans came up with? England, if you're from England, you sure would remember this. The V-2 rockets. They could launch them from Germany and bomb the mud out of England. And that was a long way away, too. They had rocketry down. We did not. Okay. And sure enough, a lot of those German scientists came over. Oppenheimer and some of those others, they helped us make the atomic bomb, too. Einstein from Germany, Switzerland and Germany. So, yeah, had a lot going on there. Well, Soviet Union got into space first. Well, we started rushing to try to catch up. And we did, and we ultimately got ahead, but it took a while. Well, NASA came into place, National Aeronautic and Space Administration, NASA. And for a while, throw the money to NASA. We need to get ahead of the Russians, the Soviets, okay? And they did. They had the money coming in. Well, once we passed them, and that's probably about the time we got to the moon first. They got into outer space first. They circled the globe first. They did a lot of things first, but we got to the moon first. So from then on, we sort of were ahead of them. Well, at that point, Congress got tired of spending so much money on NASA. So they started cutting back. And they said, you know, what they had done up till then, NASA hired the best and the brightest and the biggest scientists and stuff they could, and they were putting all the things together and stuff. They said, hey, we think you're spending too much money. Here's what we want you to do. We want you to farm out to some of these other really high-powered things like our universities, our national laboratories. They've got pretty good scientists too. Why don't you farm some of the projects out to them rather than you doing everything yourself? So they gave NASA a charge to go to Mars. Not humans, just to get a rocket to Mars. We never had gone outside the moon before, okay? So they're going to try to get to Mars. How are we going to do this? Well, you have to get other people to do your work. So you have to farm it out. They've got the labs, they've got the computers, they've got the campuses. Let them use that, and we don't have to buy it all. So sure enough, they did this. This is the first time. It was one of the early Mariner programs. They said, you have to farm it out. So they had put out bids, proposals. Okay, someone proposed on how to do the launch. Someone proposed how to get from the launch to orbit of the Earth. Someone else proposed when to leave orbit to head to Mars. Someone else do the plans for getting to Mars and going in orbit around the Mars. Okay, so that everybody had a piece. They split it up, and different ones bid on it, and they got a cheaper product. I think they got it down to maybe $6 billion. That's cheap, huh? As opposed to 20s and 30s of billion dollars if NASA had done it all themselves. So Congress was pulling the purse strings, okay? So these groups proposed and stuff, and then when they went to launch the Mariner, okay, perfect launch. Whew, it worked. Then when it got up out of Earth's orbit, it went into, out of Earth's gravitational field, went in orbit around the Earth, perfect transition. Fantastic. Okay, then when it came time, It left Earth's orbit and started heading toward Mars, intersected Mars. Perfect. I mean, that's a long way, okay? And it was a lot of calculation. Intersected it perfect. And then, when it got to Mars, it was supposed to go in orbit around the Mars. It turned and headed right to the planet and crashed. Okay? They got maybe just a few minutes of data from all that expensive equipment on there. What in the world happened? They went back and started analyzing what went wrong. Well, the group that took them from Earth to Mars was using one set of units, and the group that was taking from Mars to go in orbit was assuming they were using this other set of units. And someone had forgotten to put the unit. They put the number, but not the unit, and they assumed, and in the Navy we had a name for that. I don't know if you've heard that one before, but never mind, that they were using the same units they were, and did their calculations based on that number, and therefore it went, turned, and crashed directly into the planet because they were using different units. Units are important. I hope that you are in a position that one day you may make a $6 billion mistake, but I hope you don't make it just because you use the wrong units, okay? Most of us won't be in that position, but don't make it on using the wrong units. Sorry, that took too long. Well, let's look at some of the measurement systems we have. We're only going to consider two. There's many more out there, but these are the most common. They call this the English system, but, you know, really it's almost the American system now. It came out of England, but guess what? England is metric now. Now, if you ask any old Great Britainer, you know, that happens to be, they probably still think in terms of miles and pounds and inches and things like that. But officially, Great Britain, England, they use the metric system, officially. Okay? We're the only major industrial nation on the planet that still uses the system primarily. But I bet you y'all don't, do you?
No.
The automobiles, everything's metric now. Why? It's a global market. Most of the market is not here in the U.S. anymore. It's a global market. And if they can't get 3/4 inch nuts and bolts and stuff, they're not going to buy a car that requires 3/4 inch nuts and bolts and stuff. They won't metric. Okay? So we're slowly changing, but it's all a tough process. But it's still called the English system, even though the English don't officially use it, but they still use it on an everyday basis. Many units, and here's what's wrong with it, were based on body parts, or physical things. For instance, an inch is about the length of your thumb joint, the first joint of your thumb. Look at that, that's about an inch, okay? Now, some king somewhere in the past said, well, let's make it 3 barley corns placed end to end to end. That's going to be an inch. Guess what? If it was a real good year, maybe those barley corns were big, or a really bad year, they were pretty small. That's not a very good thing. Okay? What's another unit we use in the English system? I mentioned inch. Second? No, centimeter is metric. Foot. Guess where that comes from? Yeah, that's it. That's about a foot. A man's foot is approximately 1 foot. Some of you petite women may be a little bit shorter, and some of you maybe have. Okay, I won't go there. Okay, I'll put it this way: they didn't use Shack O'Neal when they were measuring feet. Okay, not a good idea. Okay, but yeah, guess what a yard is? Where it came from? Distance from your nose to the tip of your finger when you hold it out there. Or some king, that's what he said it would be. And guess what? Shack O'Neal, a lot further, okay? But this is a yard. Did any of you, I'm thinking the ladies more than the guys, ever go to the old hardware stores or places where they sold fabric, cloth and stuff, and you wanted, say, 3 yards of material for a dress? How did they do it? The lady there went 1, 2, 3, and then maybe did a little extra. Okay. That's how they measure yard. Now they got tables, it's all measured out to get it exact. But in the old days, did you ever see that? 1, 2, 3. Okay? That was how they did it. Oh, that's about a yard. Okay? Not the best way to have your reference. Nose to finger, that's not right. Okay? This would then be what? Fingertip to fingertip.
2 yards.
2 yards, which is how many feet? 6 feet. So that's approximately my height too, right? And that's a fact. Your wingspan here is about your height, by the way. Okay, just an interesting note. Some people are not quite with the truth. Well, they also call this a fathom, nautical fathom, 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 6 feet. Okay, not the best way to do it. Now, I'm trying to recall if I've ever heard where they got pounds and ounces from. I know I've heard somewhere in the past, but they're just as nebulous. And because they're based on such weird things, how many inches in a foot? 12. How many feet in a yard? 3. How many yards in a mile?
1,760.
Very good. Those are real common numbers, aren't they? No, there's no consistency there. Okay? How many ounces in a pound? 12? No. 16. How many pounds in a ton? 1,760? No. 2,000. Where is this coming from? It's because everything came out of different basics. Okay? So no, our system really doesn't make a lot of sense. We're used to it. We're familiar with it. It really doesn't make a lot of sense. Now, if you thought the English system was bad, England was a pretty small little country, this island here. They could maintain and keep things pretty well in control. Who was always fighting the English? Right across the channel. The French. The French and the English, they had one time they had a war. You know what the name of the war was? The 100-Year War. And that's because I guess they were always fighting each other and disagreeing with each other and at odds with each other. Did y'all ever see the movie Chariots of Fire? It was an Olympic-type movie back in the 30s or something. The English called the French the frogs. No, we can't do what the frogs do. They just always at each other. Well, but the French, they were trying to use a system. But you see, the people up in Brittany didn't really care for the people down in Normandy, and everybody hated the people that were around Paris, and they didn't like the people down from Lorraine. It's a bigger country, and they were always cheating each other. So they would change their measure. And so no one knew what to trust because they were always trying to get the odds on somebody else. Okay?
It's time to call roll.
Oh, is it? Okay. Thank you for remembering. I get carried away. What's that? Okay, let me call roll and then you can take a 5. No more. Or I could let you go on the break first and then call roll. That might be better, wouldn't it?
No.
Yeah, that would be good. That's a good idea. I'm glad you thought of that. Okay? Okay. No, I'll call roll first. I don't have it on here. I have it here. Okay. Let me learn names and faces. Zach? Is that right?
I'm ashamed.
I am too. Zach? One of you is Zach, right?
No, Zach.
Huh? You're Zach.
No, Zach's there.
He disappeared.
Zach left. I knew he sat back there somewhere. Okay, sorry. So Zach's not here. Okay. My greatest apologies here. Okay. All right. Wayne. Okay, because you came in. I remember that. Okay. Nick left.
He's going to come back though.
What's that?
He's coming back.
Oh, is he? Okay, good. Tiffany was sitting. Weren't you? Yeah, you were sitting over there. Okay. See, I don't remember faces. I remember where people sit there. James Matthew Duncan has never made it in, right? Right? Okay. Parker. Okay, got it. Okay. Lacey. No. Okay, Lacey. Oh. Yeah, okay.
I'm Lakeisha. That's what
Huh?
I'm Lakeisha.
Okay, Letitia, I remember now. Lacey. Jonathan Tristan Glaze has not made it in, right? Will. Got it, thank you. Jasmine Shante McCrae has not made it in, right? Emmanuel is right there. Okay. Siegfried. He was right there. So, no.
I'm right here.
You moved.
Well, yeah,
You're just trying to
No, sir, I just
blow
need
my
that.
mind. Okay.
You got it.
Okay, Siegfried is here. Okay. Michael. Okay, good. Thank you. Patrick. Got it. Thank you. Keisha. Got it. Philip. Okay, good. Heidi, I remember. And Amika. Okay. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 2, 4, 6, 8, 10, 12, 13. Got it. Ooh. We started with 13. We've lost people, gained people. We wound up with 13. Lucky 13. Okay, y'all need to take a 5-minute break. Please keep it 5 or less, okay? I'm going to put a pause on Screencast-O-Matic. See you back. Hopefully a few more will be making their way in. I see a few things up on that, so I think we'll. Some written books, okay. One reason I sort of don't like leaving the classroom is I get stopped in the hall. At least two. Yes, and she caught me, yeah, okay. 2 or 3 people couldn't find their classes, and of course I had to help them find that. And then the evening coordinator was looking for an instructor, and we had to talk about that some. So I need to stay in my class so I can hide. Okay. Yes. All right. So we talked about the English system. We're just beginning to talk about the metric system. That came from the French. And the reason was all different areas of France, they couldn't agree or get on the same page with having the same units because they always tried to cheat each other. Does anyone know what happened around 1791?
Yes.
What?
17.
What happened in the U.S. about that time? Not the Civil War. Come on, okay, he failed history, okay. Revolutionary War, that's the one. All right, now maybe the British considered it the Civil War, but it was the Revolutionary
It
War.
was Abraham Lincoln time.
Civil War was Abraham Lincoln's time. This was George Washington's time. Okay. Now that was 1776 is when we did the Declaration of Independence. And so the Civil War, I mean, you got me doing it now. The Revolutionary War was over by then. But who helped us? Several other countries helped us in the Revolutionary War. Who was one of the biggest? They were fighting against the British. And who didn't like the British? The French. Oh, you said French. Okay. Okay, the French. Okay. The French helped us. Y'all remember, goodness gracious, Lafayette? Oh, come on, y'all. You got to read your history. Okay. But several French helped the U.S. They were inspired by our overthrowing the British because they didn't like the British that much. And they, shortly after our Civil War, war against England, Revolutionary War, they had their own revolution, the French Revolution. Now that was a lot worse revolution than ours. They got really bloody in theirs. I mean, chopping off heads, the guillotine, you know.
Which one was that? I'm sorry.
The French Revolution.
Okay.
But in the French Revolution, they were trying to unify the country. And one of the things they did was to come up with a brand new system for measurements. And the French, this is something strange about them, most of the time they put their noun first and their adjective afterwards. We say, red chair. They say chair rouge. In other words, the chair, the tread. Okay. Well, they say system international. Rather than international system, they say system international. So when you see SI, that means system international, meaning the international system, or what we call the metric system. Now in French, metric is to measure. Metre. It's a verb, to measure. Okay? And that's the measurement system. That's all they're calling it. But we think it's the name of the system. They established this in 1791, and they said, let's get away from body parts and anything else, and let's actually use things that are fixed. So what they did, and I hope I have this right, they say the North Pole to the equator, run a straight line from North Pole to the equator, probably through Paris, France, in doing so, and take that measure, that length, and divide it by something like 10 million or something like that. That's going to be 1 meter. Okay? That's how they established. Nobody's feet, noses, arms, or anything else. They said, let's take something that's fixed. And they find that to be the unit for measure. Now, how long is a meter? Anyone got an idea? Yeah. Here's one. Most doorknobs are approximately 1 meter from the floor. I don't know why. They just are. That's about 1 meter from the floor. But if you wanted to refer to the yard, remember what the yard was?
3 feet.
Fingertip to the nose. So the meter would be about the fingertip to the opposite ear. It's about 3 and so inches more than a yard is. So it's about a yard, a little bit longer than a yard. So if you do a 100-meter dash, that's a little bit further than a 100-yard dash. They don't do 100-yard dashes anymore, but when I was in school, they did 100-yard dash and the 220s and the 440s and the 880s and the mile. They don't run those anymore. It's 100-meter dash, 200-meter dash, 400-meter run, 800-meter run, 1,600 is close to a mile. Okay.
Which is right.
What's that? Yeah, they don't even run the mile anymore. Okay. Most places don't. So that's what they did with the meter. Now, they broke a meter into, and these are the basic units, okay? And this is the SI system. They broke the meter into even things. Like we had, remember, 12 inches in a foot, 3 foot, 1760, 16 ounces, had such weird conversions. They did all their conversions based on the decimal system. So, and actually we use the decimal system some. Where do we use the decimal system? In money, right? It's a dollar or what is 1/100 of a dollar? A penny. And what do we call that? 1 cent. C-E-N-T means 100. A cent is a centy dollar. And guess what 100th of a meter is?
1 meter.
A centimeter, exactly. That means 100. Okay? A centimeter. Okay, so they broke a meter into tenths and into hundredths and into thousandths. A tenth was called a decimeter, like a decimal. A centimeter was like, a hundredth, like a cent. Okay? Or how many years in a century?
100.
100, yeah, it's based on 100. How many troops did a Roman centurion have under his command? Approximately 100, yeah. So everything, that was where that came from. Okay? Now, so they got 100th of a meter, which is a centimeter. Now, this isn't what it's based on, but just for reference, it's about the width of your little fingernail. Remember, the inch is like your thumb joint, and it takes about 2.4 centimeters to make an inch. Okay, so they're equivalent, close measurements, but not the same. Well, they took a centimeter and put a centimeter long, a centimeter wide, and a centimeter deep, and that made a cubic centimeter. Okay, 1 cubic centimeter. And in the old days, that was called a cc. They don't call it that anymore, but if you ever see cc's, if you're in medicine, my mom was a nurse, she used to say so many cc's, they meant cubic centimeters. Now they don't talk about cubic centimeters, they call them milliliters. It's the same unit, it's just a different name. But anyway, they took a cubic centimeter and they said, what's the most common material on the surface of the earth? Most common material on the surface of the earth. Say again? Actually, there's something that covers more of the earth than the ground does.
Water.
Water! Yes, the most common material on the surface of the earth is water. So let's say, let's take 1 cubic centimeter of water and take its measure, okay? And let's call that 1 gram of water. That's how much mass of water there is in 1 cubic centimeter of water. That's a pretty small amount. Little finger across and high, and that's pretty small. So it's one of those tiny little sugar cubes that really don't sweeten your coffee at all, you know. Those real little ones, okay. That was a cubic centimeter, and that was a gram. Well, a gram is an awfully small unit. Meter is a long unit. A gram is a little bitty unit. So they say we don't want to use the standard for length to be a meter and the standard for mass to be a gram. We need something bigger. So they went up, not tens of grams, not even hundreds of grams, but remember it's base 10, 1,000 grams. And what is the prefix for 1,000? What do they sell on the streets? Never mind, you should know that.
Kilo.
Oh, you know it. Okay. Okay, you shouldn't. Okay. Okay. That's 1,000 grams. Is a kilogram. So that's the basic, even though it has a metric prefix, it's the only one that does, the basic unit for mass in the metric system, the SI system, is the kilogram. I did. I set you up bad time, didn't I? Okay. All right. So that's the kilogram, basic unit of mass. Okay, now we didn't talk about mass over here in the English system, did we? What would we use to measure mass in the English system?
Inches, feet.
No, that measures length.
Yardage.
No, that's length.
Is that mass?
Mass.
Mass.
Okay, what do you say? Oh, not miles, that's length again. Okay, he said pounds.
Pounds.
Okay, not quite. Pounds measures weight, not mass. There is a difference. Later in this course, you'll know the difference between mass and weight. It's a big difference. Several big differences. But they're equivalent to each other, okay? But there is a big difference. We don't measure mass in the English system. We measure weight, but we don't measure mass. There is a unit for mass. I bet you not a single one of you has ever used it. In fact, it doesn't even have an abbreviation. Pound is LB, ounce is OZ, inch is IN, feet is FT. They all have abbreviations except this one. It's a slug. Can you imagine going in and saying, I'd like 3 slugs of celery, please? I don't think so, you know. But that's how you measure mass. We never, ever use it. We use weight. We don't use mass. In the SI system, we use mass. And that's kilogram. Now, what's the second measure? Time. That's the fundamental unit, base unit for time in the metric system, SI system. What do we use in the U.S. customary system? We use seconds also. We use seconds. That's the one thing that's common. Well, no, it's not the only thing, but that's one thing that's common. Seconds. In fact, it's so common, we don't even use good metric things there. If we're talking about fractions of a second, we talk about, in the metric system, milliseconds, microseconds, nanoseconds. You know, we use those prefixes like we're supposed to. But if you got more than 1 second, what do we measure in? Minutes. And how many seconds in a minute? 60. This is going back to English, isn't it? No, it isn't. It's actually going back to the Babylonians, not really the Babylonians, the Sumerians. They used the base 6 and 10 system. And that's why some things have 60s, okay? We went way back there. How many degrees in a circle?
360.
360. That's 6 times 60. That everything that way. That's the Sumerians. We blame that on. So the time, that's the same in both. And actually the big things, we actually use 60 seconds in a minute, 60 minutes in an hour, 24 hours in the day. Yeah, we do all those weird things like we did before. Here's another one that's the same in both. Ampere. I wonder why that's true. What does ampere measure? Current, electrical current. Okay? Why do you reckon we use the same thing English in here? Why didn't we have something different here? Because after the French came up with this, everybody said that's a great system. Except the British don't do anything the French do. Okay? Except about that same time was when electricity was being studied. Louis Ampere, for whom it was named French. Coulomb, Charles Coulomb, French. Okay? Now, Volta, he was Italian. The bolts are named after. But many of the scientists at that time were French. Okay? And they named it, and since they came along about the same time, the two sides finally agreed on something, said, we'll use the same units. So the SI units, amperes, volts, watts. Watt, by the way, he was British. He was Scottish, in fact. Okay? So they decided to use the same thing. So everything electrical, same. Isn't that nice? Your cars and your systems and all, you can all refer to the same units, electrical units. Does anyone know what this measures? Kelvin. Say again? Temperature, exactly. Now what are we used to measuring in? Degrees Fahrenheit. Okay, now was he an American or English guy? No, he was German, okay, but way before the SI system. Now, what do we usually think of being the SI unit? Celsius, but not, okay? But the Kelvin is based on Celsius. Now, why does Celsius seem more metric than Fahrenheit? What is the freezing point of water in Fahrenheit?
It's
32, nice round number, right? What's the boiling point of water in Fahrenheit? 212, another nice round number, right? How many degrees are there between 32 and 212? Oh boy, pull out the calculators. 180. 180 degrees, okay. Nice round number. Where did we get these things? Well, we'll talk about that in the temperature. But in the Celsius system, what's the freezing point of water?
32.
Zero. Celsius. And what's the boiling point of water? 100. That seems very metric to me, doesn't it? Based on 100, base 10. But it's not the best unit. And we'll talk about it later. Kelvin, a Kelvin degree, except they don't call them degrees, a Kelvin and a Celsius degree are exactly the same size. It's where you set your zero. That's the only difference. Okay?
You said Kelvin is German too?
No, actually Kelvin, the guy, Kelvin, that's not named. Oh, okay.
Okay, I just wanted to know.
Okay. Did you talk to Miss
Yeah,
Wiley?
Miss Wiley. I talked to Miss Wiley.
Are any of the students still down there?
2 or 3.
Okay, yeah.
Okay, thank you.
All right, surely.
What does he teach us?
Huh?
Does he teach us?
He teaches math. Math 98, I think this term, developmental math. That's who Miss Wiley was looking for when she came by. But I told her he's coming from a long way away, so maybe he. Yeah. So anyway, that's why he came to see me, because I'm his department chair. But let me know he did show up today. Okay, but actually Kelvin is not somebody's name. We do have an English teacher named Kelvin King, but that's not who it was named after. Okay, Kelvin is actually a title. The guy's name was William Thompson. He was British. And here is an unusual thing. He was landed aristocracy. He was Lord Kelvin, one of the few aristocrats we actually had. No, I didn't say that, did I? Okay. He was a brilliant scientist. He couldn't care less about that, but he just happened to be born into that family. So he was Lord Kelvin. They named that after him. He did a lot of the work in thermodynamics. That's why they honored him with his name. Okay, what is this? A furry little creature that digs holes in your yard?
No.
No, what is it? Huh?
It has to do with the atomic weight, don't it?
Okay, it has to do with chemical quantities, exactly. Okay? It's in some ways reminds me of a mass, but it's how much of a chemical substance you have. Not the mass of the unit, but how much chemically related. So yeah, it's a chemical unit. We're not going to deal with it in the first few chapters. We probably won't even get into the last chapter. It's a chemistry thing. Anyone know what that stands for? If you left off the A, how would you pronounce that? And what does that remind you of? Especially if you flip these two letters. This is the light of mine? No. A candle. Light. It's light intensity. That's what that measures. Yeah. Light intensity. Okay. Now, those are the 7 basic units in the SI system. Everything that you can measure in the SI system comes basically out of those 7 units. Okay? Now, I don't see anything about area there. How would we measure area with those units? Uh-huh. What is area? The area of this floor. That would be the length of this wall multiplied by the length of that wall. So that's a square meter. What if you're talking about the volume of the room? Yeah, area times height. So that would be a cubic meter. Okay, remember our cubic centimeter? Meter times, so everything else. How would you measure speed based on these?
Seconds.
Okay, it's how far you go and what time. Meters per second. Or kilometers per second, or miles per hour. That's how you do it. Basic units. Everything else you would measure is based on those 7 units. In different combinations, everything else you measure. Okay? All other units derived from those. All right. So here are the standard metric units for the 4 fundamental properties. We're going to deal with 3 of these early on, 1 later. Okay? Basic fundamental property, length. We talked about it. What do we use in the metric system? Standard unit. Not this. Meter. Okay. Okay. The basic unit in the metric system, SI unit, is meter. How about in the English system? Foot. Okay. Very good. Yeah. Okay. Well. Okay. Now, this is the metric unit, so it's a meter. What a weird way to measure it. It's the distance that light travels, because light has a fixed rate of speed. Distance light travels in 299,792,458 of a second. Yeah, you heard the TH in there, didn't you? What a weird way to measure a length. But that's officially how it's done. Okay? Okay? That's a meter. I'd rather say from my fingertip to my ear than try to remember all that. Mass, what's the basic unit of mass in the SI unit? Kilograms, exactly. And it's reference to 1 standard metal cylinder that's kept, because this is SI, in Paris, France. I think it's in the Louis Pasteur laboratory. It's kept, let's see if we got a picture of it here. No, I don't see one. I think it may be in your book. In one of the old books it was there. I don't see it in this one. So maybe in the old book it was. It's a metal cylinder that's kept in a sealed glass container on some sort of surface here, and that's in another sealed glass container, and that's in another, in a humidity controlled, temperature controlled, everything controlled room in the middle of something. No one ever goes there. Okay, so what good is that? Yeah, but then they made copies of that, and people have them. We have one at our, in the old days they called it National Bureau of Standards. Now it's called NIST, National Institute of Science and Technology. We have a copy of that cylinder somewhere in Washington, D.C., under wraps, too. But then they have lots of others that they have made copies of. Every time they make a copy, they may introduce a little error, but it's pretty close. Time, okay. Now, we measure light based on a fraction of a second, a tiny, 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 tiny little fraction of a second, but we refer to second as the oscillation of a cesium atom. Now, cesium is a radioactive element that has a very regular frequency, and based on one oscillation of that, so many oscillations of that make up 1 second. What a weird thing to do. Charge we'll do in chapter 6, okay? See electricity, okay? Everything else, volume, speed, acceleration, forces, everything else are based on not just these, but those 7 units. The charge comes up in chapter 7. Now, actually, they left off one. Temperature. They should have included temperature here. And temperature we'll get in chapter 4. Okay? So we'll worry about that. No. What was temperature? Kelvin. Kelvin. Okay? Yeah. I think that should be right up here with those. Okay. So here we're going to look at all 7 again. This SI base units. The base unit for length in the SI system, not English, is meter. Mass is kilogram. Time is second. Electric current is ampere. Y'all can read, can't you? Temperature, Kelvin. Amount of a substance, that's different from mass, but amount of a substance chemically is mole, and then luminous intensity is candela. Now, a few things to note here. Of these, only one of them has a metric prefix, and that's kilogram, because a gram was just too terribly tiny. Okay, but then the others, mass, meter, gram, seconds, mole, and candela, those are small letters. Why are amperes and Kelvin capital letters?
Okay.
What do we usually capitalize?
The beginning. No.
Of what? Say again?
A word.
Not just any word. I mean, word is W. It's not capitalized.
just their name.
Names! Okay, this was named after Louis Ampere, remember? And this was named after Lord Kelvin. So if it's named after somebody, it's usually a capital letter. If it's just like meter or gram or second, not named after somebody, lowercase. Most of the time. There's a few exceptions, but that's most of the time. And the funny thing to me, when they write the unit, even though this is almost the guy's name, they don't capitalize that or that, but they do capitalize the symbol. Strange but true. Okay. Now, the metric prefixes. It simplifies the conversion process because everything's made out of base 10. Okay? Let's just assume this is a meter. Okay? That's a lot shorter than a meter. Remember, a meter is this long. So let's assume that's a meter. And you split that into 10 equal pieces. Then, what is our system of numbers called? It's a base 10 system. We call it what do we use that dot for? Decimal. It's called a decimal system. And 1/10 of a meter is a deci, as in decimal, meter. Decimeter. Okay? So 1 meter is 10 decimeters. But if you get that decimeter and split it out and break it into 10 equal pieces, everything's base 10. Those are centimeters, because then there'd be 100 of these, because 10 of these and 10 of those, that'd be 100 of them. That's a centimeter. And then you take that little centimeter and split it into 10. Yeah, 10 equal pieces. Like you take that centimeter, your little fingernail, and 10 equal dimes there. That's a millimeter. Millimeters. Now, notice this is 10. 10 here, 10 here, 10 there. Beyond that, we don't do tens anymore. We do thousands. So the next after this is, you can say this is 1/10 of a meter, this is 1/100th of a meter, this is 1/1000th of a meter. The next thing down would be a micrometer. But a micrometer is 1,000 micrometers make 1 millimeter. You'd have to really spread this out and put 1,000 micrometers in there. Now there's another abbreviation we call that. That's a micron. Except usually when we're referring to micron, that's a thousandth of an inch is a micron. But a micrometer is a thousandth of a millimeter, which is really tiny. Now think of this. Think of that dime, and think of slicing that into 1,000 equal slices. Yeah, you're talking tiny. Okay? Very, very tiny. We'll run into that later in another context. Okay? So, this way. Now, when we go to larger units, we also, for the first three, we go by tens, but from there on, we go by thousands. Okay? So after this, it goes down to micrometers, which is a thousandth of a millimeter. In other words, it takes 1,000 micrometers to make 1 millimeter. If you got a meter here and you had 10 of these, guess what we call that? How many is 10 years? What do we call that?
Century.
A decade.
Decade.
So we would call this 10 meters would be a decameter. D-E-K-A-M-E-T-E-R. Decameter, like decade. Okay? And then if you had 10 decades, you have, okay, y'all probably aren't familiar with that. That would be 100 meters. And that would be, it starts with H, hectometer. Hectometer. Now, we don't usually use that. It's not very common, but it is a unit. But we do use it for this. Okay? What are you going to say?
Good.
All right.
The acre is used for chemicals.
What is it?
I said chemical.
What? What did you
I
say?
said chemical.
Yeah, well, what did you say
A
first?
hectare.
Okay, now a hectare, I was just going to get to that.
Okay.
Okay. How do we measure land usually? In the U.S. customary? Huh? Acres, exactly. And that's a weird, you talk about some weird thing. 52,000 square feet or something. I mean, it's a really weird, not just that, 52,800, it's a strange number. Okay. But anyway, we're used to measuring that, right? Well, in the metric system, SI system, what we would use would be either square centimeters, which would be, something like that. That's pretty small, okay? Or square meters, which would be, basically that's the area under this door. That's still nowhere close to an acre. The next biggest would be square kilometers, which would be way bigger than an acre. So what they use that's close to an acre is not a square kilometer, but a square hectometer. And if you have a hectometer squared, they sort of run that together to make it a hectare. Hectare is what they use to measure land mass, land area in the SI system. So anywhere else in the world, it's not so many things per acre, it's so many things per hectare. What?
Is that the reason why, for real, no land is actually squared? It's always.
Where is this now?
I was just saying, hectare. Is that the reason land is staked off in like an angle? Nothing is never square.
Yeah. Okay. Down where we live, yeah, it's not.
Yeah.
But if you go out Midwest, Nebraska, Iowa, they measure land in square miles. And they have what they call mile roads that define that. And then farmers would usually be doing a quarter, which is a section. A section is a quarter of a square mile. Because a square mile is huge to try to plow and do that like that. So they measure things in that. So if you get out flat areas, they do measure things in squares. Okay? But we don't around here because we have all these rivers and valleys and hills and stuff like that. And we started off much smaller than they did there. Okay. Now, what's the advantage of having all these prefixes here? If we were talking millimeters, okay, thousandths of a meter, if we were writing that in meters, that would have to be 0.001 meters. And that's a lot of decimal numbers. If we were talking kilometers, like the distance from here to Tuscaloosa would probably be, about 100 kilometers or something like that? I'm guessing. Well, that would be 100,000 meters. That's a huge number, okay? So by using the prefixes, you can have a normal number with a small unit, 1 millimeter, rather than doing 0.001 meters, 1 millimeter. So you can have a normal number with a smaller unit, okay? So it helps avoiding either very large or very small numbers by using these. But guess what? If you were dealing with mass, what would be a thousandth of a gram? A milligram. A hundredth of a gram? A centigram. Okay? 1,000 grams? We already said it. A kilogram. Okay? So everything is the same. If you're talking about current, if you have 1,000 amps, you're going to be fried, but what is that? A kiloamp. If you have 1,000th of an amp, you have this is much more common, a milliamp. So you see, all the units mean the same. You don't change when you're going from weight to length. You don't have to remember different conversions. They all mean the same. Okay? Everything's based on the power of 10. 10's a powerful number, isn't it? Okay, now, what they left off here, and I want to mention it just because it's stuff you will run into. They have a lot of things illustrated here that we talked about in class, and I'll say this at the end of every chapter when I'm encouraging you to study for the test. Let me say it at the beginning, okay? None of these slides, nothing I say takes the place of reading the book. The book has way more information than I can possibly say. I mean, I could sit here and read the book to you and couldn't finish what I need to cover, okay? Read the book, please. It's worth it. I mean, it's good stuff, okay? Whatever book you have, okay? But I did want to point out a couple of things before we move on. One of these, and I mentioned this just a little bit. Let's say that we have a block here, and this block is 1 decimeter on the side. Now let's go back to that. A decimeter, remember, a tenth of a meter. So a meter is this, right? So 1/10 of that would be maybe about something like that. Okay. A tenth of that would be 1 decimeter. So let's say we had a block 1 decimeter on the side. Okay? A cube. Okay? How many centimeters are in a decimeter? Centimeters in a decimeter. Right there. 10. 10 centimeters in a decimeter. Right there it is. 10 centimeters in a decimeter. So if this was a decimeter on a side, that would be 10 centimeters by 10 centimeters by 10 centimeters, right? And what's 10 times 10 times 10? 1,000. Very good. 1,000. And we call those, since you multiply them, cubic centimeters. Okay, remember I said this good old cc's? 1,000 cubic centimeters. Okay. That block that was 10 a decimeter, I wish I had a meter stick up here, I don't. It's about like that, so about like that, and about like this, 10 centimeters on the side. That block, that cube that, would be 1,000 cubic centimeters. So if you pulled off one of those little 1,000, that would be, remember your centimeters, centimeter by centimeter. Okay, that's 1,000 of those make up 1 cubic decimeter, or 1,000 cubic centimeters. We give a measure for that. Now, I see your bottle there. It's not quite 1, but tell me what the size of that bottle. Okay, you're talking liters. That's a fraction of a liter, like 0.6 or 0.8?
6.9.
0.9?
No, that's probably 12.
What portion of a
It's
liter?
20 fluid,
It's 20 fluid ounces.
And it doesn't give a metric?
1.25 pints.
Okay.
591 milliliters.
591 milliliters. Okay. So that's about 0.6 liters. Okay. All right. So you see a liter Coke would be almost twice that size.
If you notice the Coke bottles in the store with Walmart, it's like they got the 16.9 ounces.
Yeah.
This, you're right. I can't remember. I get them all the time.
Yeah.
But you're not getting as much Coke. You're not getting, right. The bottles are slimmer.
Yeah. Yeah. I know what you're talking about.
Yeah.
But anyway, then is what a milliliter is. 1,000 milliliters. 1,000 milliliters is the same as 1,000 cubic centimeters. So milliliter, cubic centimeter. Like I used to say, they used to measure medicines in cc's or cubic centimeters. Now they use milliliters. It's the same size, but liter measure of volume. Centimeters is a length, but when you multiply length by length by length, you get a volume. Okay. Now, this is more for you automotive guys. There was a car. Let's start with a car company. Car company that didn't originally make cars. It originally made motorcycles. So it had engines that were motorcycle size. Now, some of them pretty big hogs, but later it decided it was going to make a car. Okay? But it tried to put in this really small, lightweight car, a really big motorcycle engine, and they were trying to figure out what to name their first car. Okay? And I believe, now this sounds awfully small, but remember it originally was a motorcycle type engine. I believe it was, let me see if I can get this right. It might take me a time or two to get it. I believe it was 104 cubic centimeters. Now we would say that's milliliters. It's a pretty small engine, like a 0.1 liter engine. Okay, pretty small. But they wanted a name for this car. And I'll tell you this, it wasn't an American company, and it wasn't even an Italian company. But they chose Roman numerals to name this. And Roman numeral for 100 is, does anyone know? How many, what do you call 1/100th of a dollar? Cents. So it's a C. Anyone remember what 4 is?
4?
Yeah.
1.
No. IVCC. That's what they named their car.
It was the Chinese people.
No. Close.
Japanese.
Japanese. What do you almost read there?
The Civic.
Civic! It was a Honda Civic. Honda made motorcycles long before it made cars, right? Y'all don't remember that, but they did. That's where the Civic. Now I've heard. I don't know this for a fact, but I've heard that's where the Civic got its name.
It was like a first, like you said, they make the motorcycles.
Yeah, it was a tiny little engine.
Was it a Honda S600? No, I think that was before the Civic.
Oh, really? Was it?
I
Okay.
think it is.
Okay.
I know that car, a gallon of gas will go so far
Yeah.
on it
Yeah.
that it blew people's mind.
Yeah.
Which gas wasn't expensive then.
Right.
That first one. That first Honda
Yeah.
Civic.
Right.
The CC motor.
And that's because it was so tiny.
It
Of
was
course,
like,
how much power did it have?
yeah,
Yeah, not much. Okay. Very lightweight car. Okay. All right. Sorry about that. But I wanted to point that out. That's what a liter is, 1,000 cubic centimeters, which is the same as 1,000 milliliters, because 1,000 is a milli. Okay. Now, I think we're ready for the next. Okay. Now, understanding from measurements. And by the way, get used to this, folks. As soon as we define and do something in later chapters, then we're going to take ratios, or we're going to take, we're going to do things with it. So the first thing we do from measurement, we receive our or gather data, like measuring the length of the desk, or pencil lengths, or 25 inches, or whatever it happened to be, we record the data. Once we get that, then we start manipulating and playing around with that, okay? And one way we do is by ratios. Now, what does it mean, a ratio? Which of our arithmetic operations are you dealing with when you're dealing with a ratio? What are your 4 basic arithmetic operations? You learn them in the 1st or 2nd grade, kindergarten maybe. 4 things you did with numbers.
Add, divide, multiply, and subtract.
Exactly. Now, which one of those relates to ratios? What did you say?
Divide.
Dividing. You're absolutely right. A ratio is a division of 2 numbers. And we're going to do that repeatedly. For instance, we're going to measure lengths. Then we're going to measure the time it took to get from there to there. And then we're going to do the ratio of the length per time. Guess what we call that? Miles per hour? Say again?
Miles per hour.
What's that measure?
Speed.
Speed, exactly. Okay. So once we measure something, we're going to do a time rate of change of that and call it something else. Okay? So a ratio, dividing one thing by another. There's tons of them out there. Okay? How do we measure the pressure in your tire? Say again?
PSI.
PSI. What does that stand for? Pounds per square inch. What is a pound?
Square.
A weight measure or force measurement, and a square inch is an area measurement. So we get our weight, we get our area, pounds per square inch. That's a ratio. Okay? Okay. We'll make generalizations from those various ratios we make. The one we're going to consider now is the density ratio. Does anyone know what density ratio, what you're comparing by division? Okay, density is mass per unit volume. So that's the ratio. How much mass, kilograms, per unit volume, cubic meters or cubic centimeters. So usually if it's kilograms per cubic meter, that's going to be a huge amount. Because think about a cubic meter, this is a square meter, and come out about that far again, that's a cubic meter. If you, from the doorknob to the floor, the width of the door to where I am, if you had that mass of, say, water, guess what that's going to weigh? Approximately a ton.
Yes.
It's huge, okay? So when you're talking about how many kilograms per cubic meter, most things, that's going to be a big number. But if we're talking about smaller units, we would use what's smaller than a kilogram? In metric? Gram. And what's smaller than a cubic meter?
Meter.
Cubic centimeter. Grams per cubic centimeter. That's the one that's usually the most reasonable, because a kilograms per cubic meter is a huge number. Grams per cubic centimeter, that's a reasonable number. You know, it's usually less than 20, greater than 0.5. So that's a reasonable. Kilograms per cubic meter, thousands. Okay, so it's a big number. Now, we also use, and we'll talk about these more, symbols and equations. We'll get to that a little bit later, and then we'll talk about problem solving. If you noticed on my syllabus, I specifically made every student learning outcome solving problems. I don't know if you noticed that, but we're going to be solving problems. Okay, so let's first talk about data. It might be here, okay? So let's say, what information could you measure, say if you had a block like this, and you wanted to give a good descriptor of that block? What would you measure?
Give a description of that block.
Yeah.
You measure the length.
The length.
Time the width.
So this is probably the width times the
Time the height.
height. So that would be a good measure of that. What is the volume of the block? Okay? Well, where did you get that? You started with a length. And this is the length, and that's the length. Now this length times that length would be the face, okay? And this length by that length would be the area of that face, and this length by that length is the area of the top or the bottom. This side would be probably a lot like that, and the back would be a lot like the front. So there you have your the area of that, say, a cube. Now, if each edge of this was S, whatever that stands for, let's just call it side, the area would be, since it's a cube, what do you mean by cube? Two characteristics of a cube. The length, the width, and the height are all the same.
Right.
Okay? The other thing about a cube, they're all 90 degrees.
Okay.
Every one of those angles is 90. See, if you sat on that, you'd have something they called a rhombus or something like that, rhombohedron or something, when the angles were not other than that. That's the cube. Okay? Now, the length is S. What's the area of any side of that? If every one of these lengths is S, what's the area of a side? S times S, which is S squared. Okay? How many sides does this cube have? There's a front, there's a back, there's this right side, left side, top and bottom. How many is that?
6.
6. So then the area of the whole cube would be 6s squared. Because s squared was one side, you got 6 sides, so it would be 6s squared. Right? Well, what's the volume of the cube?
Volume is
S times S times S, which is S cubed. Right? Okay. That's just an example. Let's go over here. I should have done this one first. Measurement information used to describe the object, the conditions, like if we're talking about the conditions outside, we could talk about the temperature outside, we could talk about the wind speed outside, we could talk about various things like that. Events, okay, how long this class lasted, very short, okay, and those kinds of things. You know, we could talk about events. We could talk about changes. How about miles per hour? You know, that means how did you change your distance from home every hour you drove? Okay, that would be a change. And one example are dimensions of a cube. If each side is S, the area would be, of one face would be S squared, 6 faces would be 6x squared, and the volume of the cube would be S times S times X would be S cubed. Okay. Now, if we're looking at ratios of that, okay, now, a ratio is an analysis through a quotient of two numbers. For example, the area to volume ratio. Okay, we just said that cube that was, they're going to inches now, 1 inch. Now, most of the time, and I do this and I wish the book would, when you write the symbol for inches, I usually put a period after. That's the only unit that I put a period after. They're all abbreviations, but I only put a period there. Why would I want to put a period there?
you know, it's just an inch. It's just 1 inch.
1 inch, yeah, but here's why. If that were in a sentence,
Oh, it would say 1 inch.
yeah, and you don't know if that's a preposition or a unit. So I put the period there so you know that's a unit, you know. Without the period, to me, that could be a preposition. 1 in 5, no, 1 inch 5, you know. Which are you saying there? Okay. So that's sort of silly, but anyway. So if this cube was 1 inch on the side, okay, then its area would be, of one face would be 1 square inch, 6 faces would be 6 square inches. But the volume would be 1 cubic inch, 1 inch by 1 inch by 1 inch, okay? So the area to volume ratio, now this is a problem here I don't really care for too much. The area to volume ratio would be 6 to 1. Now in reality, you ought to have the units with it. They harped on units a minute ago, they leave them out here. But it would be square inches per cubic inch, so that's not saying a lot. But really, I think they should say it would be 6. Now let's go to a bigger square. We're going to double the size of that cube.
2 inches.
Okay? So it's 2 inches. So how big is one face of the cube? What's the area of one face of the cube? Length times width.
Width, right.
So if it's 2 inches on the side, 2 by 2 is 4. That's 4 square inches. How many sides do you have?
6.
6. 6 times 4 is?
Okay, 24.
24 square inches.
Okay,
That's the total area of the cube.
correct.
Okay? What's the volume of that cube? It's 2 inches on the side.
Right.
So it's 2 by 2 by 2.
2 times 2 is 4 times 2 is 8.
8. So it's 8 cubic inch volume. So what's the ratio of the area to volume there? 24 to 8 is
It's 3.
3. Now, isn't that something?
Yeah.
You increase the size of the cube,
Mm-hmm.
but the surface area to volume ratio is going
Down,
down.
down.
Okay? If you go up to 3 inches, what's the area of one side?
2.
3.
No, 3.
Okay, 3 per side. So what's the area of one side?
3.
3 times
3.
is 9
9.
square inches. How many sides do you have?
6.
6. 6 times 9 is
54.
54 square inches in a 3-inch cube.
Mhm.
And what's the volume of that 3-inch cube?
3.
3 by 3 by
3.
3.
9 times 3 is 27.
27 cubic inches. What's this area to volume ratio? 2. So the bigger square you get, bigger cube you get, the smaller the area to volume ratio. Okay. Interesting.
It is.
Does that make any difference?
No.
Oh, okay. Let's say that your water there had gotten sort of warm, and you asked me to go and get you some ice. Okay? I went down to the faculty lounge there, and they have some ice trays, and I get out a few cubes of ice. But I get, say, 3 grams of ice, but they're in cubes. Okay? Or I could go to the cafeteria and get crushed ice, and also get 3 grams of crushed ice.
Big differences.
Which do you want?
I want the crushed ice.
Why?
Mass.
No, the mass is exactly the same.
The area.
area.
The area of the cube, yeah, even though the mass is exactly the same, the smaller the side, the larger the area to volume ratio.
Right.
So the
Okay.
faster it's going to melt, and it's going to cool your water much faster.
Faster.
Right?
You're right.
Yeah.
That's a good example.
Okay, yeah, they have it right here.
Yeah.
Okay. I didn't make it up.
Oh, man. Yeah.
Okay.
Oh,
Now, I was in the Navy. Unfortunately, I didn't have much of this, but maybe one day or two. But in the Army, that's really famous. If you ever read Beetle Daily, that was always popular there. No one reads comics anymore, do they? Okay, never mind. Does anyone know what KP was?
What was?
KP.
KP.
What?
We always call it kitchen patrol.
Kitchen patrol is exactly what it was. You know what another name for it was?
Mess hall.
Keep peeling. No, okay, I'm sorry. Okay.
Potatoes.
Yes, exactly.
Potatoes.
Okay, now if you had to peel 5 pounds of potatoes,
Potatoes. Right.
okay, that's a pretty big job, huh?
Mom used to tell us a song about peeling potatoes.
Oh, really?
Yeah, he was.
Yeah.
I had to do carrots one time.
What's that?
I had to do carrots one time.
Okay. Now, okay, let's go down to a pound. Say a pound of carrots.
Mm-hmm.
If you had to peel a pound of carrots, and they were great big old carrots, or they were these tiny little baby carrots, which would you rather peel a pound of? The bigger ones, because guess what? The bigger the carrot, the smaller the surface area to volume ratio. So it's a lot faster peeling potatoes, or if you've got large potatoes, your surface area to volume ratio is much smaller. So you keep peeling less time. Okay, so never mind. Okay. But yeah, so here's a graphic showing that very same thing. If you have a 1 inch per side cube, then the area to volume ratio of that is
6.
6. and it goes to 3 and to 1. Okay, oh, no, I'm sorry. Okay, got it. The area, this is a tough graph to read. Okay, I'm sorry. I see it now. The 1 inch cube is this one. I don't know what that's doing there. I guess that means that. Okay, the 1 inch cube is here. Okay, the surface area for 1 inch cube is 6. So it's a little bit more than halfway up to 10. Okay, the volume is a tenth of the way up to 10, but the area to volume ratio is again 6. Okay. Then they go to the 2 inches on the side. Its surface area is 24, so a little bit, almost, they don't show it well, but about halfway up to there. Its volume is 8, so that's just less, but the surface area to volume ratio is even smaller. That's 3, okay? But then when you go to the 3 inch cube, the area's got quite a bit bigger. The volume got quite a bit bigger, but the ratio is still getting smaller. So that's what that graph's about. So rather strange looking, but to me the graph does nothing. This table says it all. Okay, I can see what the graph's saying, but it takes more time to figure out what it's saying than to say, oh yeah, that makes sense. Right. And guess what? We will be doing this in lab. Okay, something like this. Not exactly, but close. So now let's look at the density ratio. As I said before, the density ratio is a ratio of mass per unit volume. Okay? Now, why would we worry? Why don't we just deal with mass or just deal with volume? Why would we want to make a ratio, the density ratio? Did you ever hear the old joke, which weighs more, a pound of gold or a pound of feathers? Say again?
They're equal.
They're equal because they both weigh a pound. Well, what did you think? You thought a pound of gold is small, a pound of feather is huge, but the weight is a pound is a pound is a pound, right? Okay, so you were really thinking density, really, when you were thinking. Now, here is a story, and this supposedly was true. Whether all of it's true or not, I'm not sure. But there was a very famous Greek mathematician and scientist. His name was Archimedes. Archimedes. He's known for flotation, that kind of stuff. He's known for a lot of things. I mean, that guy came up with inventions BC that were amazing. BC. I mean, he was like 400, 500, 600 BC, way back. And he came up with things we still use today. Have you ever used an auger, like to lift grain or something like this? You know what it's called? An Archimedes screw. He developed that. He invented that.
Really?
How many thousands of years ago? Okay? Amazing character. Okay. All right. He was a great scientist, and his king really loved him because he came up with all sorts of things. He came up with ways to defeat bigger armies and navies than they could possibly handle.
Yeah.
And one thing he did, he got mirrors and put them up on the mountain. And, ships were wooden back then. And he got concave mirrors and focused the mirror on the ships when they were coming around to attack. And that focused.
They were saying bigger ships.
Yeah, well, actually, it concentrated the light so much that it heated it up and burned them. Wow. And he burned the ships before they ever got there. And then the gunpowder flew off. I mean, it's just, he was amazing. No, his king really liked him. Well, this king had a rival king that he didn't trust. He didn't really like too much. But they were trying to get along, and this rival king gave him this big, beautiful, ornately designed crown. And he said, "It's my gift to you." Well, this king, Archimedes' king, didn't trust him. He said, "How do I know this is really gold? It's gold on the outside, but is it really gold all the way through? Archimedes, come here, figure that out for me." Yeah. He pulled out his pocket. "Oh, no. I don't want it scratched, because if it's pure gold, I don't want any fault to it. I want you to figure this out without damaging the crown." Archimedes said, "This is tough." So he decided, he was thinking about it, always thinking about it, and back then they had the public baths, okay? And he went to clean up one day and went into the water, and he happened to notice, of course, when he went into the water level came up, right? That happens. And he said, of course. In fact, the word he used was eureka. I've got it. That's what it means. And he was so excited, he had figured out how to tell if the crown was pure gold or not. Because you might have, let's just be extravagant, 3 kilograms of gold. That doesn't tell you much except how much mass you have. You may have so many cubic centimeters of gold. That doesn't tell you very much. But one thing that's true, the ratio of mass to volume for gold is always the same. Always the same. In fact, of every material, it's unique. It's an intrinsic property independent of how much you have. You can have an ounce of gold, its density is going to be the same as if you have a pound of gold. The volume will be different, the thing, but the ratio will be the same. And Archimedes said, I've got it, eureka. All we have to do is measure the mass of the crown and then sink it in water and see how much water comes out. That will be the volume of the gold. We can measure how much water comes out. We can take the ratio and we know whether it's gold or whether it's gold with iron in the middle. You know, because iron has a different density than gold. Now, supposedly, this is the part I don't know about, he was so excited about figuring this out, he jumped out of the bath and went running to tell the king.
No clothes.
With no clothes on. But, you know, he was a scientist. They were crazy, you know. You got to watch these physicists there. Could do anything. Right? Hey. All right. I'm not going to do that. Okay. It's an intrinsic property of the material. It's a characteristic of a given material. So if you know the mass and the volume, which are usually easy things to do, calculate the density, and then you can say, hey, this is pure copper or it's not pure copper. What's the likelihood of that penny being pure copper? Not.
Zero.
Okay?
Zero.
Yeah. Because it used to be that quantity of copper was worth a penny.
Exactly.
Now that quantity of copper is worth a lot more than a penny, so they mix other things that are much cheaper to try to get it closer to a penny's worth. Okay? So no, it's not. And remember, they did that with the quarters quite a while ago. You'll never see a quarter that doesn't have a strange color on the edge, because that's not really silver or nickel or any other valuable thing. It's cheap metal. It's just coated to look like gold. Yeah.
That's what sometimes when they get stuck in a Coke machine.
Yeah.
It's that thing.
Yeah.
You put a real quarter in there.
It may or may not work anymore because they've gained it. Okay. Now, because here in the U.S., in the English system, we don't have a unit for mass, remember? Well, what was that unit? Slug. Okay, we don't use that. So we use what they call weight density, which is weight per unit volume or pounds per unit volume. And that's why our pressure is pounds per square inch. Because, well, no, that needs to be a weight anyway. So don't forget that, okay. Well, we use weight density. Now, here's that density ratio. The density, the mass density, is usually given now. What does that look like? A P. It's not a P. A P usually has a little head on it like that, you know, a little edge on it. This doesn't have the edge. That is the Greek symbol rho. Why they use rho, I don't know, but they use it. And the density is mass per unit volume. Okay. Now, rho is a lowercase Greek symbol. Mass. Okay. Now here's something I hesitate to even say this, but I'm afraid if I don't say it, it might be confusing. We use letters for an awful lot of things. We use them for units, and we also use them for what I call parameters, to stand for something else. This M is standing for mass, because it starts with M. The same M, if it was following a number, would mean meter. Okay, so don't get confused the letters. If it has a number before it, it's a unit, and that would be meters. If it's just in an equation or a formula, then that's a symbol or a parameter that stands for mass. Okay? Little m here. Why in the world would we use a capital V for volume? Why don't we use a little?
It represents a name.
What's that?
Somebody's name.
No, it's not somebody's name. That's a good try, though. Here's the other reason for that. Okay? And this is not a unit. This is a symbol. This is a parameter. Here's why. Later, like in the next chapter or two, we will start talking about something else that starts with V. Anyone make a guess of what that is? Second?
Voltage.
Okay, no, volt. Okay, volt is capital V2 because it's named after Volta, named after somebody. But that's a unit. Okay? It's also a parameter too, and unfortunately that's capital V2. But before we get to volts, the next chapter we refer to as close to day. Distance per time is distance per time. Distance per time. We talked about it earlier. Distance divided by time. Distance measured in feet per second or miles per hour. What's that measure? No, miles per hour measures
Speed.
speed. Okay? Now what's another word for speed that we use sometimes? Velocity. That's your little v. Parameter, little v means velocity, capital means v means volume. Oh, we use the same letters over and over and over for so many different things, and then later we'll use them for volts too. So you're absolutely right, voltage. But in this case, this is volume. Capital V is volume, little v is velocity. Capital T will stand for temperature.
Right.
Little t will stand for
Time.
time, exactly. So you have to get used to these things. So this is our mass ratio, rho, which is density, is equal to mass per unit volume. Okay? Now, here we have cubic centimeters of each of these things. 1 cubic meter of gold has a mass of 19.3 grams.
Okay.
Always. When Archimedes was going to measure that, if it didn't come up 19.3 grams per cubic centimeter, if it came up anything else, it was just gold on the outside, something cheaper on the inside. That's how he did it. If it was iron on the inside, that's only 7.9 grams per cubic centimeter. So if it was somewhere between 8 and 19, it probably had iron in it, or something else. Water, now remember water? That's what we first measured a gram by. 1 cubic centimeter was exactly gram. So that's exact. That's our standard. In fact, water is our standard for so many things. We'll see it over and over and over. That's our 1 gram per cubic centimeter. Air, on the other hand, a cubic centimeter of air is 0.0013 grams. That's 10/thousandths of a gram. Pretty small. Okay. So these are examples of that. So this just shows also, if you know the density of something, you have a real good idea of knowing what material it is. If you have the table. And they do have a table with, oh, yuck. I forgot this. How are we doing on time, by the way?
17.
Second?
17.
7:10. Oh, we've got plenty of time. Okay.
Yes. Yes.
What
Yes.
my computer has it though. Well, I haven't pulled it up. Okay. I meant to go over this table. I started to, and then I got off into something else.
Okay.
It's really quick. Let's look at these metric prefixes. We did the 1/10, which is deci, 100th, which is centi. This is on page 6 in my book. If you got a book, it's somewhere around there. It's table 1.2. In my book, it's a green table. See if you can find it. Oh, you got it. Right, okay. 100th is centi, 1,000th is milli, 1 millionth is micro. Now, again, we've got symbol problems here, folks. Huh? I know. And I'm going to do it on this page. So we had our base unit. Let me see. Is my pen activated? No, it's not. Oh, where's my pen? Why isn't it? Oh, there it comes up. Okay, now I got it. Okay. You've got your basic unit. Okay. There we go. Now, what do you want to be the basic unit? You could use meters, you could use grams, you could use amperes, you could use any metric unit you want. What you want to use? Meter. Okay. You said meter?
Meters.
Okay, meter. So this is 1 meter. A tenth of that would be a decimeter. A tenth of that, which would be 100th of a meter, would be a centimeter. A tenth of that, which would be 1,000th of a meter, would be a millimeter. Now we have 2 M's. The first one's the prefix, the second one's the unit. Okay? Then we go to powers of 3. The next one is micrometer. This is milli, and the next one is micro. Well, guess what? We've already used little m. So what are we going to use for that prefix? Well, guess what? We go to the Greek alphabet, and the little m there is called a mu. It looks like a U, but that's the letter mu. So that would be a micrometer, or microns. Okay? Then, that's 10 to the minus 6. This is 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. That's 1,000th of a micron. That would be a 9 nanometer. That's nm. Okay? Now, have y'all heard about or read about nanotechnology? You're talking things really, really tiny. When you're down in the nanometer range, you're smaller than the size of an atom. You're getting that small. Okay? And guess what? They get smaller. Okay? 10 to the minus 12 is pico. Okay? That's a picometer. Now, I've never dealt with anything that small, of course, or never could see it if I could. But for 8 years, I worked at Southern Research Institute in radon research. Radon is a radioactive gas, and it's radioactive. It's naturally occurring. It's everywhere, but there's not much of it unless you trap it somewhere, as in a basement. Or you just happen to be near a uranium mine or something else that puts out this gas. It comes from radium, uranium, radium, and then radon. It's a radioactive gas, but it's a gas, so it's colorless, odorless. You can't tell it's there. How they measure it is because it's radioactive, they can measure the radioactive decay. And radiation is pretty dangerous stuff. So even though it's so small, what they measure it in is picocuries, which is the amount of radiation. 10 to the minus 12th of a curie per liter. 4 picocuries per liter is enough to cause you problems, as in maybe lung cancer or something, if you breathe it for a long time. Tiny, tiny amounts. That's the only time I've used pico. It's picocuries per liter. Okay? But 10 to the minus 15, that's a prefix called femto. F-E-M-T-O. And that's a femtometer, or femtocurie, or whatever. And the only place I've ever, and I remember that 15, that's 10 to the minus 15, by the way. The minus is part of the 10. You can't see it. There it is. Okay. 15 femto. I remember it that way. The only place I've ever used it, the company that made equipment to measure picocuries, they said they could get down to femto level. So they were Femtotech is what they named the company. That's the only way I remember that. Okay? But then you can get even smaller than that. 10 to the minus 18, and this is just so tiny, I can't imagine it. And that is an atto. A-T-T-O. I've never seen anything measured in this. That would be an attometer. It looks like AM. Okay, attometer. Okay. Or attogram or attocurie or whatever. Let's get on the bigger end. Well, bigger than a meter, 10 meters. What's 10 years? Decade. So this is a deca. Now, this book calls it a DA. I've seen other books that call it DK. I think DA is probably a bit more common. That would be a DAM, which sounds like something that holds back water. Okay? Okay. Here comes snickering. It sounds like a time for a dumb joke. No?
No.
You don't want a dumb joke. I can't believe that.
Sure, I do.
I want to hear a dumb joke.
Okay.
I want to hear a dumb joke.
What did the fish say when it swam into a concrete wall?
Oh, so wait.
Repeat
Say
the
that
joke.
again.
What did the fish say when it swam into a concrete wall?
Damn.
Oh, okay. This is about as risque as I get. Okay, never mind. All right. That's enough of that. That's the only one of these that has 3 letters, by the way. Okay, then 100. What do we call 100? This was 10. 100 is 10 squared. That was the hecto. H-E-C-T-O. Remember hectare? And that's a hectometer. Oh, I put it in the wrong place. So a hectometer. And 1,000 was? Kilo. Okay, you remember the street, don't you? Okay, never mind. Kilometer. Okay. All right. Then we go up by powers of 3. That was 10 to the 3rd. So 10 to the 6th, we go up by powers of 3 now. Anyone know what that's a mega. M-E-G-A. Now, we've already used little m and little Greek m. What are we going to use for mega? No, a big M, capital M. That's a megameter, capital M. Okay, good thought though. Now, because we started using capitals now, these are the prefixes, not the thing. We're going to use capitals from now on as you get bigger. So the big units have capital letters after the M. That's a megameter. Okay? Now, I've never used megameter really to measure anything, but I have used, and I think you have used, what do you measure your computers in? Memory.
Gigabytes.
Okay. In the old days, I remember when they bragged, we have 10 kilobytes of memory. They used to brag on that. Then they went up to megabytes. Now they're up to, what's the next one? Giga. So this is 10 to the 6.
They're above gigabytes.
Yes, they are. 10 to the 6 is giga. And that would be capital G meters. 10 to the 9th. Oh, no, that was 10 to the 9th. This is 10 to the 12th. That is, anyone know what that is?
10 to the 9th?
No, 12. 10 to the 9th was giga.
Terra.
Tera. Okay? 12 is tera. T-T, okay? T-E-R-A. And they do talk about terabytes now.
Yes.
And terahertz, too, I think. So things that are very, very fast. So that's as fast as I've heard of, but they do still have 2 bigger ones. 10 to the 15th is, I don't ever use it, so I have to look it up. Peta or peta, I don't know which that is. Peta, I don't know. And that would be capital P meters, if that's what we're doing. And 10 to the 18th would then be exa, E-X-A. I've not seen anything in that, but EXA, sorry about that. Okay, exameter. I wanted to throw that out there just to remind you or familiarize you. Big units use capital prefixes after the mega. Okay, 10 to, this is a million, a billion, a trillion, whatever follows a trillion. What is it?
Quadrillion.
Quadrillion and then quintillion. Ooh, big numbers. Okay. What's that? Yeah, it's that many dollars, right. Oh, it would ruin you, wouldn't it? Okay. You're ready to be ruined, I can tell. Okay. When we were talking about these these densities here, that's why I started looking at the table and realized I'd skipped that one. Table 1.3 on whatever page that is, maybe around 9 or so. This gives some of the common materials. Aluminum is about 2.7, now they're using the smaller units, grams per cubic centimeters. That's the handiest thing to use for density in my mind. Copper, much denser, 8.96, almost 9 grams per cubic centimeters. Believe it or not, copper is denser than iron. Iron is 7.87, almost 8 grams per cubic centimeter. Lead, really, really dense, 11.4 grams per cubic centimeter. Water, of course, that's our standard. Why? 1.00 grams per cubic. Now, seawater is a little denser. Why would that be true?
Because of the salt.
Because salt is dissolved in it, and salt is denser than water, so it's being a little bit more. Now, what's the ramification of that? Have you ever been in a boat that was, say, used in fresh water and salt water? Okay? If you have, you might notice on the bow of the boat, somewhere there, they have the gradation. It shows how deep the water line is, what it's called. And in salt water, it'll rise up higher than it will in fresh water because of the greater density of salt water. Okay? So boats that travel in both will have 2 water lines on them, one for fresh water and one for salt water. Now, have you ever swum in salt water?
Horrible.
Huh?
It's horrible.
Well, in your eyes and in your mouth and stuff. But what do you notice about floating?
It's easy to float.
Much easier because salt water is denser. Archimedes' principle. You float here. They say Salt Lake City, which is even denser than most seawater, you float even higher. And the place that's the densest water, the Dead Sea, you can hardly sink, and you don't want to either, because I think it stinks like crazy. But I've never been there. Yeah, it's pretty bad stuff, but you can't walk on it, but you float really high in it. So, now, believe it or not, when I was in college, I was a sinker. I didn't know I wasn't a swimmer, but I actually, later my wife said she realized that because I'm really dense, but never mind, we won't go there. But, now, here they list another metal, and this metal is mercury. What's different about mercury?
The weight.
Okay, it's very dense, 13.6 grams per cubic centimeter. But what else is different about mercury from most other metals? It's a liquid. Under normal conditions, it's a liquid. So guess what? Lead, which is 11.4 grams per cubic centimeter, if you drop it in a pool of mercury, which is 13.6 grams per cubic centimeter, lead floats. You never thought you'd ever see lead float, right? But don't try it. Why not? Mercury is very poisonous. It's a carcinogen. You don't want to. And I can remember when I was in school, kids would get a little bit of mercury, they'd break a thermometer or something like that, and then they'd put a penny in mercury, and it would look all shiny like a dime, and it was all, and they were handling it like crazy. They were absorbing all that in their skin. No wonder they were, no. Okay. All right. Gasoline is 0.680. What's the ramification of that? The density is 0.680, 68 hundredths or 680 thousandths of a gram per cubic centimeter. It's what? Have you ever? Say again? It's lighter than water, so therefore what does it do? It floats on top. Therefore, the Gulf oil spill, you remember that one? That wasn't before your time. All that oil and stuff washed onto the beaches, okay? Because it floated on the water. What a mess. And those poor birds and other wildlife got coated with it. Okay. Now, the book also has some of these little blurbs in it. They're called Concepts Applied. those are pretty interesting. Sharks and cans, okay? Cola cans, I'm sorry. I'm from the South, I call them Coke cans. Okay. Here is an example here, and let's take advantage of it since we got it. Now the trouble is, there's just not much room to write on these slides. Okay, there was one. What I'm going to do is erase everything on the slides. And by the way, I can't, this thing, I think my computer's getting tired too. Okay, let's look at example 1. We got time?
I don't think so.
Oh, yeah, I already heard that, yeah. Huh?
Yeah.
Okay. Example 1.1 that's on my book is at the bottom of page 9, first column, but it may be somewhere else in yours. 2 blocks are on a table. Now I draw ugly tables, but let's just imagine this is the table. Okay, there's your table back there. Okay, 2 blocks are on the table. There's a block. Now that's not much of a block. Block A has a volume of 30 cubic centimeters. This is block A. Its volume, capital V, is 30.0 cubic centimeters. Okay? That's the volume of block A, V sub A. Okay? It has a mass, so the mass of this, that's little m sub A, it has a mass of 81 kilograms. 81.0 kilograms. That's its mass. Block B over here, a bigger block, maybe that's why it's B. Block B has a volume, so the volume of B here is 50.0 cubic centimeters. Okay? And it has a mass, so we'll call that MB, is 135 grams. Whoa. All right. Which block has the greater density?
Have the same.
Why do you say that?
I have no idea.
Okay. All right. How would you determine that? What's the density of block A? What's the symbol for density? It's not a P, it's a rho. Rho of A would be, what's the formula for it? Density, mass of A over volume of A. Okay, the mass of A was 81.0 kilograms divided by the volume of A was 30.0 cubic centimeters. Now let's just take a break for just a second here. These shouldn't be kilograms, they should be grams. Grams, I'm sorry. This is gram. I messed that up. Let me... Okay. Okay. Now, just a second here. What are these extra zeros doing on here? Why does that say 81.0 grams and 30.0 centimeters? What is that extra zero? Why is that in there? Is that even necessary?
It could be.
Huh?
It could be if there's something there, like if it was 31.2.
Yeah. But what does it mean to be 0.0? Okay. What that means is a more precise measurement than 30. 30 would be its 30 centimeters, cubic centimeters to the closest centimeter. 30.0 means to the closest tenth of a centimeter is 30.0. That means it's a more precise measurement. You have 3 digits of precision everywhere. That's why they only put 135 here and didn't put a decimal. You got 3 degrees, 3 units of precision there. All of those are 3 units of precision. So when we do this division here, 30 will go, has anyone got a calculator? 81.0 divided by 30.0, you don't have to put the point zeros there. What do you get?
Say
81 divided by 30.
81 divided by 30.
You could do that.
2.7.
2.7, but actually we said 2.70 grams per cubic centimeter. Why should we put a 0 there? You got 3 digits going in, you get 3 digits coming out.
Right.
You can't get 5 digits out if you only have 3 in, but when you put 3 in every place, you ought to get 3 out. So you should put that. Let's do the density of B. What's the rho for B would be mass for B over volume for B. What's the mass of B? 135 grams over 50.0 cubic centimeters. Cubic, okay. And what does that come out being? 2.7 what? 0 grams per cubic centimeter. Okay? That tells you two things. No, you said it right on the money, same density. What else does that tell you? They must be the same material. Let's see what material that might be. Look at your table. And you see anything 2.70? Aluminum. The odds are huge that that's aluminum because density is an intrinsic property. It's the characteristic of the material. So the real good chance those are aluminum blocks. They're just different sizes, but they're both aluminum. See how nice it is to know how to calculate densities. Okay, they did the same thing. Have we got time for 1.2? What's the time?
Sir.
Huh?
Set 8 o'clock.
Ah!
33.
You got a time.
It's what?
7:30.
Oh, we got time for 1.2. Okay. All right. A rock with a volume of 4.50 cubic centimeters. So here we have an old rock here. The volume of this rock is 4.50 cubic centimeter. Okay. Has a mass, so the mass of this rock is equal to 15.0 grams. What is the density of the rock? Density of the rock would be mass of the rock, M divided by V. Mass of the rock divided by volume of the rock.
Excuse me, so 5.
No, 15.
15.0
Grams divided by
divided by 4.5
cubic centimeters.
squared.
Cubic centimeters. And what would that come up being? Got a calculator?
Yeah.
Anyone got a calculator? Say again? No, 15 divided by 4.5.
Yeah.
3.33.
Okay, and
Is
that's
it? Yeah, 3.33 grams per cubic
so
centimeter.
what is it close to?
Okay, now that's a rock, and a rock is a little denser than aluminum. They don't list silicon on here, but it would probably be between aluminum and silicon, or maybe, certainly between aluminum and iron. Okay, so
Oh my God, yeah.
yeah,
Yeah.
okay,
Because iron is 7.
Yeah.
7.9.
yeah, it's really dense. Okay, now let me mention this one other thing, or two other things. One, notice I didn't just give 2.70. I put my units. Don't forget to put your units. Those are important. Okay? And let's see. It seemed like there's something else I thought of, but I can't remember it now. Okay. Let's just do a quick other thing or two. Another concept applied. How dense is your textbook? How would you determine that?
The
The mass.
Yeah, put it on a scale and get the mass in grams.
The grams.
Now, I wouldn't put this underwater. That will mess up your thing. So, but you could measure length by width by thickness in centimeters and come up with volume in centimeters, mass divided by volume. You could do either and see every day. Okay? And then, now this is usually sort of fun, most of these. Myths, mistakes, and misunderstandings. They have these in the book too, and they're usually pretty interesting. All right. Now that looks like maybe a good stopping point. We'll begin next time at symbols and equations. Sorry about letting you go early. I promise not to refund any of your dollars, okay?
No, it's all right.
I hate to cheat you out of your tuition dollars. It makes me feel so
If
bad.
you want to let us go even earlier than
Oh, no. Oh, please. Perish the thought. Okay. You too, thanks. Good class, y'all.
I appreciate it.
So,